Uh, Hello, everyone. I welcome Dr. Om Pal, sir. He has joined us for the keynote, Ministry of Electronics and Information Technology. Hi, sir.
Hello, sir.
How are you, sir?
Sir, I'm fine. How are you?
I'm fine, sir. Thank you. So we will start your keynote by 3. Just waiting to finish 2 more sessions.
Sure, sir.
Kavya? Kavya?
Yes,
I
sir.
think we can start. Kavya, I think we can start. It is already 3.
Yes, sir. Let's start.
Yeah.
A very good afternoon. I, Kavya, warmly welcome you to the second day of the ICICC-2021, the International Conference on Innovative Computing and Communication, organized by Shaheed Sukhdev College of Business Studies, University of Delhi. Supported by Universal Innovator in association with National Institute of Technology, Patna, and the University of Valladolid, Spain. Sponsored by Springer AISC Series, Elsevier SSRN Series, SRGE Scientific Research Group, Egypt, SETIT Sciences and Technology of Image and Telecommunications, Tunisia, Ministry of Electronics and Information Technology, Digital India, National Productivity Council, SGRT, Scientific Group of Research and Technology, Publication Partner, IEEE, Springer, Elsevier, Wiley, MDPI, IndoScience. I feel very proud to say that the first day of our scientific program was indeed a huge success. In the inauguration yesterday, we were blessed with the presence of our esteemed chief guest, Dr. K.K. Agarwal Sir, Chairman, NBA, guest of honor, Dr. Suresh Jain Sir, National Secretary, Bharat Vikas Parishad, General Chair, Professor Siddhartha Bhattacharya, Christ University, India, Deputy Director, NITP, Professor Suresh Kant Verma, Principal of SSCBS, Dr. Poonam Verma, Chairperson, SSCBS Governing Body, Dr. Kavita A. Sharma, Convener, Dr. Samir Sir, SSCBS Delhi, Convener, Dr. Ashish Khanna Sir, MATE, Delhi, Dr. Ajay Jaiswal Sir, SSCBS Delhi, Gulshan Sir, and Mulchand Sir. All the mentioned delegates enriched the attendees, participants with their precious views. And it did not end here. We also got the opportunity to attend keynote sessions by Professor Oscar Castillo, Tijuana University of Technology, Mexico, and also Professor Anuji Agarwal, University of Delhi. We saw 104 paper presentations from all over the globe and saw the best of the best being awarded at the UILA award ceremony. I'm sure we're all very excited about what's coming up next. So without any further ado, we have with us Dr. Om Pal Sir, scientist at the Ministry of Electronics and Information Technology, Government of India. Dr. Om Pal Sir received BE in Computer Science and Engineering from Dr. B.R. Ambedkar University, Agra. He has an MBA in Operation Management from IGNOU, MS Research in the field of cryptography from IIT Bombay, and PhD in the field of cryptographic key management from Jamia Millia Islamia, New Delhi, and a Visvesarya PhD fellowship scheme of MEITY. He has 15 years of academic and research experience in various areas of computer science. He is currently a scientist D at the Ministry of Electronics and Information Technology. He has evolved and worked on many research projects of national interest. His present role includes the drafting of R&D policies, monitoring the progress of R&D projects, screening, shortlisting, evaluation of new R&D proposals, etc. Previously, he has worked at the Center for Development of Advanced Computing as a senior technical officer and as an IT resource person in National Thermal Power Corporation, NTPC. During his tenure at CDAC, he has taught various academic subjects along with research activities. He has filed patents on conditional access systems and cryptographic systems. He has also published many research papers in international journals and international conferences of repute. He has been nominated on the board of reviewers of various peer-reviewed and referred journals. His research interests includes cryptography, quantum cryptography, cybersecurity, blockchain technology, theoretical computer science, and cyber laws. We warmly welcome you, sir. It's over to you. Thank you.
Good afternoon, and thank you very much for invitation in this conference. Now I am sharing my screen. Okay. Is it visible to everyone?
Yes, sir, it is visible. Yes, sir.
Okay. So, topic for this session is quantum computing and quantum cryptography. So, first, before moving on quantum computing and quantum cryptography, first we will see what is classical computing and what is the need, why we are moving from classical computing to quantum computing. And before this, just we will see one example. There are 2 points, point A and point B, and a person want to move from point A to point B, but person is not aware about the water transport as well as air transport. So he has only one choice. First, he has to go on to point C, then from point C to point B. But in this case, a lot of time is needed. So if he can devise any other means of transport like water transport or air transport, in that case, he can save a lot of time. So just like this example, quantum computing and classical computing, actually these two theories, these two approaches are totally different from one another. Means solving mechanism of quantum computing and solving mechanism of classical computing is totally different from one another. So just we see what is quantum computer. A quantum computer is a machine that performs calculations based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. Okay. In case of classical computing, we store information 0 and 1 by using transistors. Transistors store information either in on or off state. If state is on, then we say it is 1. If state is off, then we say it is 0. So means we represent information either in 0 or in 1. Means we have only 2 choices for any bit. But in quantum computing, there is something else other than 0 and 1. So we will see what is other than this. In quantum, we can use physical property of a quantum particle, like spin up, spin down. Let there is a electron, then we can represent 1 as a spin up, we can represent 0 as spin down. Other than this spin up and spin down, there are some other cases in which we can also represent the information other than 0 and 1. We will see. Okay, for polarization, we can also represent the information in form of polarized light. If light is polarized vertically, then we can represent, then say if the polarized light is vertical, then we say it is 1. If it is horizontally polarized, then we can encode the information as 0. So means by using this mechanism, we can transmit the information 0 and 1 by vertical polarization and or by horizontal polarization. Now, if the angle is between 0 and 90, if the angle is 0, then we say that it's a horizontal polarization. If the angle is 90, then we say it's the vertical polarization. If the angle is between 0 and 90, let 45 degree or 70 degree. If the angle is 70 degree, then we can't say with 100% surety that it is 0 or it is 1. Okay, so as I said, there are many ways, means we can represent the information by using the physical object in quantum scenario. If the nuclear spin, let orientation of atoms nucleus in magnetic field. If it is in upward direction, then we say it is 0. Or in quantum term, we say cat 0. Cat 0. In classical, we represent the information by unit bit, but in quantum we use qubit for representing this information. If the position is downward, then we say it is cat 1. Okay, so actually cat, this is just a representation. It is called a cat 0. It is called cat 1. So actually it's a direct notation. Okay, so in same way, we want to represent the information in 0 and 1 by using the states of an atom. If it's a ground state, then we say it is 0. Let it's excited state, then we can say it's 1. Okay, now representation of data qubit. So as I said, cat 0, cat 1, these are two basic states, or we can say these are two basis states, cat 0, cat 1. If the probability of cat 0 is 1, then we on measurement we will get 0. If the probability of cat 1 is 1, then on measurement we will get 1. So if the probability between 0 and 1 for any bit, means cat 0 or cat 1, then always we will not get 0 or 1. So now what are the valid state? Alpha cat 0 plus beta cat 1. So actually this is the valid state. So here what is alpha and beta? Actually alpha is the probabilistic amplitude of cat 0 and beta is the probabilistic amplitude of cat 1. Here the total probability alpha square plus beta square equal 1. So if the value of alpha square is 1, it means probability of cat 0 is 1. So if we measure any quantum state with probability alpha square 1, then always we will measure cat 0. So if the probability of cat 1 means beta square equal 1, it means alpha square equal 0. In that case, always we will get cat1. Now, so other than this cat0 and cat1, what is other than this quantum particle may remain in a third state, which is neither excited state nor ground state. Means it's not cat0, not cat1, means something else. Means it's not let the spin of electron, it's not at 90 degree, not at 0 degree. Means at let the angle is 45 degree or let 60 degree. In that case, if we measure this state, then sometimes we get 0, sometimes we get 1. Now, what actually the beauty of this quantum theory is this: on these superposition states, means this third state, alpha 0 plus beta 1, where for superposition state, value of alpha square and value of beta square lies between 0 and 1, means not exactly 0, not exactly 1. So here the state psi, let the state is psi equal alpha 0 plus beta 1. So this is the superposition state. So calculations, means computations, can be performed on these superposition states. But in classical computing, we perform calculations on 0 and 1 states only. But in quantum theory, we can represent many valid states between 0 degree to 90 degree. So means on these many valid states, computation can be done. Means after doing calculations on these superposition states, then we can measure the result and we will get the probabilistic value. Means we can't say that always we will get the measurement as 0 or measurement as 1. Means it is a probabilistic result. If the orientation, let the degree is 90 degree, then it is near to cat 0. It means the value of alpha square is not exactly to 1, but is near 1. So in maximum cases, when we measure this quantum state, we will get 0. But in few cases, we will get 1 because the angle is 80 degree. So, but in classical computing, there is no probabilistic result like this. Other than this, there is another term, multi-qubit. It means we can represent a multi-qubit by using more than 1 qubit. In this, there are 2 qubit, qubit 1 and qubit 2. Qubit 1 alpha 0 plus beta 1, and there is qubit 2 gamma 0 plus eta 1. Now, these 2 qubits are in superposition state. So now in form of superposition vector, we can see a qubit by mixing these qubit 1 and qubit 2, and on this superposition vector state, we can perform the calculations. Now, what is quantum entanglement? So, entanglement is the ability of quantum states to exhibit correlations between 2 or more objects, even though the individual objects may be especially separated. Means in quantum theory, if we entangled 2 quantum states, if we entangled 2 particles, then if one particle is in our galaxy and another entangled particle is in another galaxy, then if we change the orientation of one particle, or we change the movement of one particle, then suddenly, means immediately, reverse effect happened on another means that entangled particle. Let there is a one electron in our galaxy and another electron in another galaxy. So if the position of electron in our galaxy is upward and position of entangled electron is downward, then if we change the position of electron in our galaxy, then immediately the position of second electron changed from downward to upward. So here we see this change is happened more. Actually, this change is happened with speed more than the speed of light. Actually, so if we change the position of one electron, then without any movement, we see the change in another electron. Now, like the classical computing, there are gates in quantum theory also. So, what is quantum gate? Actually, it is a setup of quantum mechanical equipments which converts the present quantum state of a quantum particle into a new quantum state. So, actually, this is an arrangement. If we give input of a quantum particle, means let vertically polarized light, then if we pass this polarized light from this quantum setup, then we see the output in a horizontal polarized or in at a particular angle. So after passing the gate, we see the change in the quantum state. So just to be talk about first gate of this quantum gate, a gate which operates on 2 qubit is called a controlled NOT gate, or we say C0 gate. If the bit of the control line is 1, then it inverts the bit of target line. So there are 2 bit, A target bit and B control bit. So if the value of B control bit is 1, then it inverts the value of A target bit. This is called the C0 gate. Now, next gate, simplest gate, involves 1 qubit and is called a head-marked gate. Actually, this is most useful gate in quantum computing. By using this head-marked gate, quantum bit shifts from base state to superposition state. So if we want to transfer the, or we want to shift the quantum state from base state to valid state, base state to superposition state, then we use this head-marked. So this head-marked gate is represented by H. So if we provide the input as a cat 0 in this for this head-marked gate, then we get the superposition state as cat 0 plus cat 1 by root 2. It is also called cat plus. So after this, if we apply another head-marked gate on this output, then we see, then we get the same result as our input cat 0. So there is one more thing. If we apply cat 0 on this head-marked gate, and we get cat 0 plus cat 1 by root 2. Now, before giving input, this input into second head-marked gate, if we measure this value, then we get exactly, means 50 in 50% cases 0 and in 50% cases 1. Now, if we apply cat 1 as input in head-marked gate, then we get cat 0 minus cat 1 by root 2. This state, this superposition state, is also called cat minus. Now, so in classical computing, there is no perfect random number generation algorithm. But in quantum computing, by using head-marked gate, we can get the perfect random number So how we use this head-mod gate? Just we see. First, apply cat0 for this head-mod gate. Then what we will get? Cat0 plus cat1 y root 2 means this is cat plus state. Now, actually, this is the superposition state. So now, if we measure this cat plus state on this measurement, we get equal probability of cat0 and cat1. Means in 50% cases we get 0, and in 50% cases we get 1. In Qiskit, we can do programming for this circuit like this: QC equal quantum circuit 1 means here we apply 1 qubit QC dot H0. Here for this head-mod gate, just we are supplying cat0 as an input, then QC measure all. Now by using this statement, just we are measuring the value, then job execute QC backend equal Quasum simulator sorts equal 1000 means 1000 times just we run this circuit. Now after plotting this diagram, what we are getting? We are getting the probability of cat0 49.7% and probability of 1 is 50.33%. Now now we talk about the power of quantum computing and classical computing. Quantum computing operations are reversible, but as we know, classical computing operations are irreversible. All qubits can be operated simultaneously, hence exponential speed up is guaranteed. Also we saw that we can do calculations on superposition states, and there is no concept of superposition state in classical computing. So there is additional advantage in quantum computing. We can perform the calculation on superposition state. Superposition states represents a new state in quantum computing. As we so more numbers can be stored in qubits and compared to classical bits. Now before coming on actual problems, just we will see one problem, and that problem is solvable in exponential time complexity in classical computing, but in quantum computing that problem could be solved in polynomial time. So now before coming that problem, just we see some fundamentals. There is a function UF. For this function UF, just we are supplying 2 qubit cat x and cat y. After applying input cat x cat y on this function UF, what we are getting? Just we are getting cat x y XOR cat y XOR fx. If we apply y equal 0, in that case, what will be value? Cat x cat fx. If the value of y means value of target line is 1, here actually x is control line and y is target line. Now if the value of y is 1, then what we are getting as an output of target line? Complement of fx means on control line the qubit is x, which is same as input, but here we are getting the complement of fx. Here x belongs to 0 to power n, means the length of x is n. Now what is function? The mapping of function is 0, 1 to 0, 1. If the function is constant, then fx equal 0. In this case, what will be the output? UF cat x cat y, we will get cat x y XOR fx. It means cat x cat y. It means we are getting the same result. If the function is fx equal 1, means fx is a constant function. We assume that fx is a constant function, then always it returns fx equal 1. In this case, what will be the output? Output will be cat x, cat y dash. It means just we are getting complement of y on target line. What on control line, just we are getting x. Okay, now we will use these things. Okay, now there is a problem. That problem is called the Divorce problem. There is a function fx, and just we want to check whether function fx is a constant function or a balanced function. Actually, from a trusted source, we got the information that function fx is a balanced function or a constant function. We are sure that from these two category, function fx is balanced or constant. What is the meaning of balance and constant? If we are getting the same result at each time, is for all inputs, if we are getting the same result, then fx is a constant function. And if in 50% cases we are getting a result, there are two possible results, 0 and 1. If in 50% cases, if we are getting fx equal 0, and in other 50% cases we are getting fx equal 1, then we say that this function is a balanced function. Now, if we use classical computing, then how many queries are required for determining whether fx is a constant function or fx is a balanced function? If the length of string, length of x is n, in that case, what are the total possible values? 2 to power n. So half of 2 to power n is 2 to power n minus 1. So means at least up to 2 to power n minus 1 times you have to query the function. Means up to 2 to power n minus 1 times you have to give input to fx and check the output. Means up to 2 to power n minus 1 time, if you are getting the same result, then still you can't say that this function is a balanced function or constant function. It is possible that on next run it gives the output as 0. Then you can say, okay, this is a constant function, because there is no need to further check, because from a trusted source we know that it is either balanced or constant. But for this classical case, we need at least 2 to power n minus 1 plus 1 queries to determine whether this function is a constant or balanced function. Now, in quantum computing, the approach means the methodology of determining this function constant or balanced is different from this classical, and only in one query, means only one query is sufficient to check whether this function is a is a constant function or not. So here we are seeing that this problem, the complexity of this problem is exponential complexity, but in quantum computing, just we are able to solve this problem in polynomial time. So as I said, to certify that function is constant, 2 to power n minus 1 plus 1 number of queries are needed in classical computing. So actually, this is the circuit. Here, these are partitions: partition A, partition B, partition C, D. H is the Hadamard gate. UF is a function. Here, just we are applying cat 0 on this first Hadamard gate, cat 0 on the second Hadamard gate. After applying these two qubits on these two Hadamard gate, then on this point A, what we will get at step A, here we are applying cat 0, cat 0. These two head mod H tensor H. Now what we are getting, cat plus means cat. What is cat plus? Just we saw the cat plus is nothing but cat 0 plus cat 1 upon root 2. So here we are getting superposition state. After applying cat 0 in head mod gate H, we are getting the superposition state cat 0 plus cat 1 upon root 2. It means cat plus. And same state we are getting after this second head mod gate. Now come at step B. Transform I tensor Z. I actually it's a identity gate. It doesn't convert the quantum state from present position. Z is a phase shift gate. It shifts the current state to another state. So is applied to the state cat plus. So I apply at cat plus, we get the same result at point B. But this second cat plus is applied on this gate Z. So here what we get, this gate Z converts this cat plus to cat minus. So here we are getting cat plus cat minus. Now target qubit is in minus cat minus state. So control state is cat plus as it is. What the target is Z change the superposition state of this target state from cat plus to cat minus. So presently we are at point B. Now we supply this input to function UF. So at step C, UF is applied to state cat plus cat minus. So here definition UF cat x cat minus minus 1 to the power fx cat x cat minus. So here first is cat plus. Cat plus means cat 0 plus cat 1 upon root 2 cat minus. After supplying this, what we are getting? We are getting minus 1 to the power f0 cat 0 plus minus 1 to the power f1 cat 1 upon square root 2 and cat minus. So what is the output of this? Means at target line we are the qubit is cat minus, but what is this at control line? So here after this UF gate we are applying another head mod gate on this after step C. So after applying head mod gate at this step, what we will get? So if the function f0 is constant, it means in both cases value of f0 and f1 is equal. If the value is equal, then what we will get? It means here we will get cat 0 plus cat 1 upon root 2 means cat plus. We will get cat plus cat minus. First bit is cat plus, second is cat minus. Now if the f0 is not equal to f1, then what we will get? Then we will get cat 0 minus cat 1 upon root 2. It means cat minus cat minus. Then control line is cat minus. So after this, what we will get after applying the head mod gate on this? Cat 1 cat minus. But in if the f0 equal f1, then what we will get? Cat 0 cat minus. Means only in single query. If we here what we are seeing at control line, the output bit is cat 0 if f0 equal f1, and it is cat 1 if f0 is not equal to f1. So here by applying by one query, just we are able to check the function whether it is constant or balanced. So in polynomial time we are able to determine the nature of the function, but in classical computing it's not possible. For that exponential complexity is required. So next, what is Deutsch-Jozsa algorithm? in actually, this is the extended version of that Deutsch algorithm. Previously, the in X in input just be supplied only 1 qubit. Here we extended n number of qubit for X, and the nature of function is same. Just we have to determine the function is balanced or constant. So just we are, I'm not going deep for this algorithm. Okay, now just we will see quantum cryptography. In previous slides, we saw that how problems can be solved in polynomial time which are not solvable in classical computing. Now, what is asymmetric encryption? In asymmetric encryption, we use 2 keys. One is called public key, another is called the private key. So if we encrypt anything by public key, then we can easily decrypt by using the private key. So first we see what is RSA algorithm. After this, we will see how this algorithm could be, how this algorithm can be break by using quantum computing. So algorithm is first select 2 number P and Q. After this, we compute n equal P into Q. After this, phi n equal P minus 1, Q minus 1 means these are steps. Then randomly select encryption key E. Then compute private key, decryption key D. So these are the steps. So now this is the encryption and decryption. I'm not going in detail. Just we see how we can crack this algorithm. So main step in this algorithm is n equal P into Q. P and Q, these 2 numbers are secret number. So if attacker is able to factor number n, if attacker can get P and Q, then easily he can compute phi n, and after using phi n and E, he can compute decryption key D easily. So what is the attack, quantum attack on this? Actually, by using quantum computing, by using SOR algorithm, in 1994, SOR invented an algorithm, and by using this algorithm, RSA step n equal PQ. This n can be factored in polynomial time. So by using this algorithm, actually in quantum computing, the main challenge, or we can say the main problem, is the implementation of the algorithm, means stability of the system. So stability of the quantum state, coherence of the quantum state. So if we can stabilize the system for large numbers, then we can factor n very easily for large values. Okay. Now another algorithm is Grover's algorithm. In 1996, Grover invented this algorithm. In classical computing, just there are records in a database, 10,000 records, and we want to search a particular record. And then in average case, total number of steps means 5,000 steps are required. But Grover invented this algorithm. By using this algorithm, this quantum algorithm, any element could be searched in root n times. So it means root of 10,000 means only 100. So in classical computing, 5,000 steps are needed, but in quantum computing, only 100 steps are required. Okay, so this is the comparison. So RSA algorithm, it's not secure in quantum scenario. ECC also not secured. AES, DES, these are symmetric algorithm. Symmetric cryptographic systems, these are secured in quantum scenario. what Grover algorithm is the threat for this symmetric. Actually, it reduces the strength by half. So we have to take the length of key double. In that case, we can avoid that Grover search. Okay. So like P and NP, P problem, NP problem, we can categorize the problem which are solvable in polynomial term by quantum computing as a BQP. So now we see quantum key distribution. Before coming at quantum key distribution, just to see what is Diffie-Hellman. So just I'm not going in detail. Detailed step of Diffie-Hellman. First user A sends something to B, then B apply its secret on this, then B compute the key. In same scenario, A compute the key. So security issue, in classical protocol, no true randomness in generator symmetric key. System based on discrete algorithm are not safe under quantum attack, man-in-middle attack. RSA algorithm as well as digital signature, which are based on RSA concepts, they are not secured in quantum scenario. Now we see what is quantum key distribution. Heisenberg's uncertainty principle states that it is not possible to measure the momentum and position of a quantum particle with absolute precision. Non-cloning theorem states that it is impossible to make the identical copies of any quantum state. These two principles are used in quantum key distribution. Quantum cryptography is the photon particle on different bases of quantum key distribution, polarized light. So this is the first quantum key distribution protocol, and it was published in a conference in Bangalore in '84. Here, Alice sent the stream of photons on different angles on 4 polarized state: 0 degree, 45 degree, 90 degree, 135 degree, and Bob measures these photon particles by using two detector bases, rectilinear basis and diagonal basis. In rectilinear basis, this filter just catch 0 degree photon and 90 degree photon. So in diagonal basis, it catches the photon at 45 degree and 135 degree. But the main beauty of this algorithm is this: Bob measures the incoming stream of photons on random basis. Bob doesn't know on what basis Alice sent this photon. If the base is correct, if Alice sent at 0 degree and Bob measures by using rectilinear filter, then measurement is correct. If Bob uses diagonal basis, then measurement is wrong. So after completing these steps, then Bob shares the basis to Alice on open channel. Then Alice says that these are the correct bases and these are the incorrect bases. So they discard the all particles for which Bob measured at wrong basis. Now, if any intruder is between Alice and Bob, if let Eve is there, in that case, Eve is also not able to figure out the stream of this key. Means he is also not able to figure out the key. Actually, Bob, that Eve doesn't know. Means if the measurement is diagonal, then it is 45 degree or 135 degree. So if he measures wrongly, then quantum state is changed. By that Heisenberg principle, if he measures wrongly, then quantum state change. So in that case, Bob will get wrong result, and that result will not match to Alice. It means they discard the key. So the what are the major quantum key distribution challenges? Set up an error-free key distributing environment. It's a major challenge. Another, actually, the implementation miss, or we say hardware challenge. In 2010, Lederson et al. Proved that in principle, BBIT4 protocol is unconditionally secure, but secret key can be figured out if the hardware implementation is faulty. Also, there are some other implementation attacks. Okay, in 2016, NIST launched this quantum resistant signatures, quantum attack resistance algorithm campaign. In this first round, out of 69 received proposals, 26 were selected, and in round 2, 9 proposals were selected. Finally, in round 3, there are 3 quantum attack resistant digital signature algorithm. So in future, we will see who is the winner for this. Now, we see progress of quantum computing. In last 20 years, in 98, IBM, Oxford, they built quantum computing of 2 qubit. Then in 2000, progress was 5 qubit. In 2019, Rigetti announced in August 2018, it would release a 128 qubit quantum computer in next 12 months. So this is the progress, but they could not release a 128 qubit. But in last on 23rd October 2019, Google claimed that Google has claimed the quantum supremacy and announced the development of 53 qubit quantum computer. And Google also claimed that task that can be completed in 10,000 years on a fastest supercomputer of IBM. And that task they completed only in 200 seconds. So this is the complexity, means how classical complexity can be converted in a polynomial time complexity. So also there are many other players like Intel, Microsoft, etc. Okay, so what are the possible applications of quantum computing? There are many possible applications. Means actually for weather forecasting, molecular comparison, and simulation of chemical reactions, we use the supercomputer. So still we want to build a more powerful supercomputer, because just we want to do the computation fast. So if we can use the quantum computing strategy approach, then I think all these problems can be tackled in very easily. So there are many other applications in machine learning, logistics, bio, informatics, finance, etc. So basically, we divide the quantum technology into 4 parts: quantum communication, post-quantum cryptography. Actually, this is the basically theoretical branch. Quantum computing, development of algorithm, quantum sensing, development of sensors, etc. So here we see the overall development of quantum computing. In quantum computing, United States is a leading country. In quantum cryptography, China; quantum sensors, United States. And in this quantum key distribution, China is leading. So we have to take little bit post to come in this list. Quantum computing research status in India. As we know that Indian government already announced a budget of 8,000 crore in 2020-21. So for 5 years, companies like IBM, India, Lab, these are the major companies which are working in quantum technology in India. In 2017, DST launched the Quantum Mission Program, Quest, and other institutes like the TIFR, IASER, ISC Bangalore, these are working in this domain. So what are the implementing approaches? Actually, major challenge in quantum computing is the implementation. Actually, theoretical research is not a challenge. So how we can handle the quantum states, movement of the electron, movement of the quantum particle, at a superposition level. So this ion trap approach, ions charged particles are confined in free space using electromagnetic field. Neutral atom approach, cool down atoms and trap and control environment. Actually, the overall challenge is to how to control the quantum particle. So as we say, what are the other quantum challenges? Attacks on publicly cryptography system. As we see, if SOR algorithm is implemented for large bits, then RSA is not safe. Development of reliable quantum hardware, this is a challenge. Development of quantum standards, this is also a challenge. Transformation from classical to quantum infra. Practical implementation, unethical use of quantum cloud services to break classical system. So hackers, hacking, breaking of classical system, this is also the challenge, because attackers may utilize quantum computing power for many unethical use. MIT's initiatives, MIT also granted some projects in quantum field, design development of quantum computing toolkit, post-quantum digital signature for document signing, creation of COE. These are some major projects. Future directions, manpower development program need to be initiated at various engineering and science institutions in the country. We can initiate short-term as well as long-term. Content on quantum security may be added at UG and PG level to develop manpower in quantum programming. Training on quantum programming languages like QSAR, Qiskit, Quantum Development Kit, it could be provided to the students. Brainstorming sessions. Other than this, device development, focus area should be R&D on quantum materials, quantum sensors. Actually, major challenge the implementation. So first we should tackle this. Other focus area, quantum algorithm, quantum key distribution, multi-party quantum key distribution, post-quantum digital signature, parallelism and Grover's algorithm, quantum languages, quantum compiler, etc. Now, questions, please.
The participants may feel free to put their questions in the chat box, or they may unmute themselves. If there are no further questions, I think that we should end this. Shall we?
No questions.
Sir, please share email ID with the authors. So if there anyone have any question, any doubt, then he can mail you.
Yes.
That will be great, sir. Yes.
Okay, sir. So
okay, sir. Thank you. We got your email ID in the chat box. If anybody is having any question, then they can free to mail him.
Sure.
Thank you so much, sir.
Thank you so much, sir, for this insightful session on quantum computing and quantum cryptography. We're very happy to host you, sir. Thank you.
Thank you. Thank you.
It gives me immense pleasure to introduce our next keynote session speaker, Dr. Syed Ali Mirjalili. He is the Associate Professor and the Director of the Center for Artificial Intelligence Research and Optimization at Torrens University, Australia. He is internationally recognized for his advances in swarm intelligence and optimization, including the first set of algorithms from a synthetic intelligence standpoint, a radical departure from how natural systems are typically understood, and a systematic design framework to reliably benchmark, evaluate, and propose computationally cheap, robust optimization algorithms. He has published over 200 publications with over 25,000 citations and an H index of 57. As the most cited researcher in robust optimization, he is in the list of 1% highly cited researchers and named as one of the most influential researchers by the world by Web of Science in 2019 and also in 2020. Dr. Mirjalili is a senior member of IEEE and an associate editor of several leading AI journals, including Neurocomputing, Applied Soft Computing, Advances in Engineering Softwares, Applied Intelligence, and IEEE Access. His research interests include robust optimization, engineering optimization, multi-object optimization, swarm intelligence, evolutionary algorithm, and artificial neural networks. He's working on the application of multi-objective and robust meta-heuristic optimization techniques as well. Thank you so much, sir, for joining in today. It's over to you.
Thank you very much for the great introduction. Hello, everyone, and welcome to this session. I would like to first extend a warm welcome all the way from Brisbane, Australia. Here is 8:30 p.m. We had a great sunny day. It's pretty late here, but I'm very excited and I've got a bit of energy left. So, and so hopefully we're going to have a fantastic session together. Before I get started, I would like to also thank the organization committee of this fantastic conference for the invitation. I've been to India, I think, three times. So I visited 3 beautiful cities. It's always my pleasure to share a little bit of my knowledge with my small knowledge with a great Indian researcher. In the field of AI optimization, we have great leaders, leading researchers. Most of leading researchers are from India, and it's always good to be a part of these kind of events. So what I'm going to talk about today is optimization problems and algorithms. Okay. Well, the way that I usually run these kind of sessions, which is supposed to be keynote speech, is a little bit different, to be honest. And that's mainly because I usually don't have enough information about the demographic of audience, which is fine. So I try to make the slides as informative as possible and as easy as possible. So hopefully by the end of today's session, there will be a little bit of takeaway for anyone, whether you are working in the field of AI optimization or not. I am pretty sure you will find a few takeaways, good takeaways from my talk today. A bit of background about where I come from and what I do. So I'm the director of a center called Center for Artificial Intelligence Research and Optimization. A lot of academics have the luxury of inheriting a research center and a research group from other senior academics. But I think I was lucky enough to build my own team and my own research center. So I'm the founding director of this center. And you can see the keyword optimization in the title. That's a part of DNA, which is also my DNA. We are very good in a couple of areas, broad areas, machine learning and optimization. we've been able to collaborate with a wide range of research, wide range of academics across the globe. And this, the map on the right-hand side shows some the universities and countries that we've had project. And by the end of this talk, if you see, if you find if that excites your interest, please get in touch with me. I've got my email and my website too as well. You can get in touch with me, and I'll be happy to connect you with someone in my team, or even across the globe. For any possible collaboration. So as I said, I'm going to be talking about optimization problems and algorithms. And the reason why I start with a problem but not the algorithm is because to be able to use an optimization problem, and usually optimization algorithms are tools to solve a problem, right? And often the question that I get asked a lot from people, whether face-to-face, online, by email. So they come to us and say, what's the best algorithm in 2021? What are the best techniques? And the first thing that I respond is okay, what's your problem? Because if I don't know your problem, okay, if we don't know what sort of problem you're trying to solve, we cannot find a solution, right? We cannot find an optimization algorithm. And then the analogy that I always give to people is a bunch of locks and keys, right? As an optimization algorithm expert, my team, play the role of a keysmith, right? We can develop a wide range, we can build a wide range of keys. But when you come to us and say, okay, I want to open my door, I cannot, give you a magical key out of my pocket so that you can open all keys, all locks, I should say. So that's why what we do, we will sit down with our client, whether from the industry or collaborators from, different institutions. First, the first thing that I get them to do is to, talk about the problems, okay? And that's what I'm planning to do. I don't know if you can see my mouse, hopefully yes. So I'll get them to talk about and list the inputs, output, objectives, constraints, and that's what I'm going to do at the beginning of this, in the first half of this talk. I will take you through the main component of any optimization algorithm, problem, I should say. And from a small problem that might take a few seconds to solve to a massive optimization problem that might take, months to optimize, they all, they can be simplified into those 3 or 4 components. So I'll talk about them first. After we have a good understanding of those problems and we know what we expect people, then we can sit down and say, okay, this is your key, this is your lock, I should say, and here's the right key for your problem. Okay. So yeah, sure. I got a private message saying to share my email. I will do that after we finish this this talk. Okay, so let's get started with optimization problems. So as I said, any optimization problem, whether big or small, whether finding the optimal path from Earth to Mars and land Prosperity rover, to a very small problem of finding the optimal length for the table, they all they have the same structure, okay, at the foundational level. Any system, so I'm going to call it a system, not even a problem, because it might be a simulator, it might be a mechanical machine, it might be anything that you would like to optimize. We have a set of inputs on the left-hand side, as you can see. So these are the variables. We call them decision variables, parameters. But I use a generic term called inputs because the system, doesn't work without them. We provide the system with the input. And what does the system do? The system calculate one or multiple outputs. What is the output? Often we call the outputs objectives, cost functions, and fitness function, and so on. But I use a generic term called output because regardless of the whether it's a cost, whether it's a performance, whether it's efficiency, doesn't matter. It is an output coming out of the system. Okay. Then there is also some constraints, right? These are the constraints that we have to deal with. They are usually applied to the inputs. It can be as simple as a range of the parameter or the input, or it can be, you know, a very complicated mathematical equation restriction the one part of, you know, your simulation, or one part of the system. And we have to bond, we are bound to those constraints, which means if we violate those constraints, even if we find the best solution, it's not desirable, right? So these, and after identifying those three inputs, right, again, any problem can be, you know, broken into these three components. So if you have a problem, optimization problem, the very first thing that I highly recommend you to do is to grab a paper, draw a table, 3 rows. Row number 1, list the inputs. Row number 2, list the outputs. Row number 3, list the constraints. The order doesn't matter as long as you identify them. And I'll talk about the later on, probably in the next 10 to 15 minutes. I will show you the what's called the challenges that you might face, and the complexity that we deal with when it comes to the inputs, outputs, or constraints. And after we identify these, we can formulate the problem. Okay, without the loss of generality, I will formulate it as a minimization problem. What I'm saying here, minimize f x1, x2 to xn. Those are all the inputs to this function, which is the output, subject to not violating those constraints. Okay, and after we do that, after we finish doing that or formulating our problem, we can now employ an optimization algorithm to solve the problem or to optimize the problem. So what is an optimization algorithm? Is nothing than, you know, a piece of, you know, algorithm or piece of program that, you know, fine-tune the inputs while listening to the outputs and constraints. Okay, you can, even when you manually change something with the hope to maximize or minimize something, you are doing an optimization yourself. Okay, and that's what we do also in our everyday life. Like when you want to catch a bus, or when you want to go from your home to your university or to your work, usually what you do, without unconsciously, you try to find the fastest road, right? You decide, okay, it's gonna be a traffic, so I go by walk. That kind of decision making is for a goal, right? To get to the university faster. If it's raining, then that might change. You might say, okay, I'm gonna get an Uber or something, because of the constraints that you're dealing with, because it's raining, right? You don't want to get wet when you don't want to get wet, basically. So what I'm trying to say is that optimization problems are everywhere, right? We are surrounded by optimization problems, and any field that you touch on, I'm sure, if you think about it, whatever field you are working on, image processing, robot path planning, even in the fields of, you know, physics, chemistry, people are trying to improve something, all right, increase or decrease something, and that's why optimization algorithms are very popular, because people need them. People don't want to solve the problem manually, and because of the complexity of the optimization problems, we cannot do them manually. In the past, yes, we had small size problems, so we could do them manually. But that's not the case anymore. The complexity of the problems keeps getting bigger and bigger every year. Now, to put that in perspective and show you what happened, I've got a mosquito flying around. Hopefully you can't hear. So what I was trying to say is that to just put that in perspective, I'm a very visual person. I love data visualization, and I believe that, you know, when you visualize things, you can better convey the message. And that's why you will probably see a lot of visualization, sometimes a little bit cartoonish, but hopefully, you know, that makes it a bit easier to understand the concept. So now I want to show you what this when you create input, when you identify inputs, outputs, and constraints, what happens? What you are trying to do? We are trying to create a search space, define the search space, but how does that search space look like? That's what I'm going to show you now. Let's say I want to optimize the length and width of this table. Okay, I don't care about the number of legs. I don't care about the thickness of the table, the material, nothing at the moment, just 2 parameters, the length of the table and the width. So let's formulate this problem. As I said, we have to sit down and think about the inputs. So I've got 2 inputs, length and width. I assume that both of them can change from 1 to 10. Okay, what's the output? Remember, the output is also important. Let's say I want to minimize the weight, or I don't know, stress, or whatever, any sort of output, I assume we want to minimize the weight of this table. Okay, so and I assume again, this is just a conceptual example. There is no physical equation behind it. I know it's very trivial, but it serves its purpose. I purposely kept it fairly simple, just so I can easily visualize the search space for you. So I assume the weight is a function of length and width, obviously. So I added length and width multiplied by 1, and I give, let's say, 1 kilogram per unit, something along those lines. What about the constraints? As I said, constraints are usually can be applied to any part of the system, but I assume now, okay, although length and width can be changed from 1 to 10, I assume length should be between 2 and 7, or even I can write, I want length to be sharp, 1, or let's say 4 or 6. This is an assumption that you make, and usually you're not as an optimization expert, we don't make an assumption. We have clients who will tell us, I want a table this size. They give us that sort of, constraint to work with. So now we've got these constraints and the objective and the inputs, we can formulate the problem. We're going to minimize the weight of this table, which is a function of length and width, subject to not violating those two conditions. Okay. So let's see what we've done just now. As I said, I'm a very visual person, so let's visualize what we are trying to do, what sort of problem we are trying to solve. The x-axis represent width, the y-axis represent length, and the z-axis represent the objective. I wish I used different color. I might just do it quickly now. So that's green, the output is green, and those two are blue, which are the parameters. So this is called search landscape, right? I haven't visualized it, but what we are trying to do, we are trying to see, okay, when I change length and width, how much weight will change, okay? So let's just start with width and length both equal to 10, change 1 to 9, and make both of them 9, okay? So we are going to end up with 4 points in this space, right? That's 10 and 10, 9, 10, 10, 9, and that's 9 and 9. And again, of course, it's a continuous space, so that can be changed to 9.5, but I make it simple. Let's just forget about, any sort of continuous value. If I keep doing that, if I keep changing width and length, I'm going to get 8 more tables, 50 more tables, and 100 tables. So think about it. If I take 10 values for the width, 10 values for the length, I multiply them, there are 100 different table designs that I have to choose from, right? Which one is the best one at the moment? Remember, we are trying to minimize the weight, so that's the best one, okay? But remember, I haven't applied, first of all, the variables are not discrete, they are continuous. So even this small problem has an infinite number of solutions, which means there are, we can't count them. There are, an infinite number of solutions in this search space. And I haven't even applied the constraints. If I apply the constraints, they shrink, usually they shrink the search space. So now with considering the constraints, that's no longer a valid solution, although that tick the box of minimizing the weight, but we don't like it because the client doesn't want that. So the best solution for this simple problem is the one down here, which is where width and length are both equal to 1. I know this is a very simple problem. Linear problem because there is no local solution. We have one global solution, the minimum down here. And to be honest, any sort of optimization algorithm, even gradient descent, any basic optimization, any sort of optimization problem will be able to easily find the global optimum or the best solution. But remember, in reality, the problems are not that easy, right? This is just a conceptual example, again, just a conceptual search space. Again, I still assume there are 2 variables, right? But in reality, usually we've got thousands of variables, right? And in that case, one of the issues that we have is that we cannot visualize it to say, okay, that's the best solution. So I cannot point and say, here it is. So high dimensional problems are a challenge. We can't visualize them. That doesn't mean we cannot solve them. But what I'm trying to say is that keeping in mind that if you're solving a 10-dimensional problem, a problem with 10 variables, you are searching in a 10-dimensional search space. We can't visualize it, but it's there. There is a 10-dimensional space. I wish we could visualize it really, but we can't. But it's there, ready, and there is one best solution down there, somewhere in that 10-dimensional space, ready to be discovered. Okay. The output, we have one output, but we may have multiple outputs. I'm going to talk about it in a moment. But think about it. I might have multiple of these with different shapes. So this time, I'm not looking for one solution. I'm looking for multiple solutions. And the constraints can be so complicated. For the example that I gave you for the table, it was very simple. But look at this one. I've got gaps. I've got even, separated. It will separate the entire search space. So those are the regions that we don't like and we don't search at all. We try to avoid them as much as we can. If you look at this problem, of course, we can visually see this is the best problem because of the heat map. That's probably the best, where X is, I don't know, 4.5 something, Y is minus 1 point something. Okay. Now, this is probably where the main part of my talk begins. And that's because I'm going to now talk about the challenges that people face when it comes to the inputs, right? It's not always as easy as, a bunch of parameters. Usually, the first challenge and the most common challenge is the large number of decision variables. As I said, the more variables you have, the more dimensions you will have in your search space, and the more permutation. For that two-dimensional problem, the problem has already infinite number of solutions. Now think about the size of that sort of search space and the growth. The size of problem grows exponentially, as you know, with adding any number of input. That doesn't mean we can't solve them. Look, the word record using evolutionary algorithm and stochastic optimization algorithm is 1 billion variables. So we can, of course, but what I'm trying to say is that you need to have some strategy. You cannot grab one optimization algorithm off the shelf and apply to a problem with tens of thousands of parameters and expect that it gives you the best results. There are some fine tuning. What are the approaches here? I don't get into the details, but if you're interested, what the literature that you have to look into is called larger scale optimization, which is where we find, we try to help the algorithm to find the dependency between the variables. Sometimes we have correlated variables. It's very similar to feature selection. You need to sometimes do some pre-processing to make the search space a bit smaller. Sometimes the algorithm you need to do some sort of algorithmic changes to be able to solve these kind of problems. That's not my area. I've done a bit of work in the past with people, but not my area of expertise. But there is research going on. We've got research centers. So that's one popular subfield of optimization called larger scale optimization. You might have variables with different ranges. My example was a square shape. See, this example is a square shaped search space, right? It is a squared because I've got 10 and 10, but usually it's not the case. The range is different. Sometimes then that you will then end up with a rectangular search space instead of or I should say hyper rectangular because it's an n-dimensional search space. There might be dependency between the inputs. For example, if I change it, that might change other ones, and that's important understanding. And the algorithm needs to know, or needs to at least discover that sort of relationship. Sometimes we can understand that sort of dependencies after optimization with post-processing the result, but there is also mechanisms how to do this at the algorithmic level. Discrete variables, some problems are binary or discrete. This is where you need to use a binary version of the algorithm or a combinatorial optimization algorithm, right? So it's different, right? The search space might seems to be smaller, but remember we have state space explosion. Same concept. By adding any discrete variables, you're going to grow the size of search space exponentially. You can have mixed integer. You can have mixed integer or mixed variables. Some of your variables might be continuous. Some of them might be binary, which is very annoying, I know, but that's a reality. Usually, look, I've been involved in a real world project. Usually you are going to deal with a mix of them. And that means you can't grab off the shelf algorithm and expect it to work. So you need to have a bit of algorithmic change, or at least get someone to do that sort of changes for you. Noisy outputs, noisy inputs, I should say. That's one of my main area of expertise. My PhD was on robust optimization, which is an area of optimization that looks not only for optimal solution, but also robust, which means imagine if I design an aircraft, the wing of an aircraft, and say, okay, the optimal length is, I don't know, 20 meters. Okay. During the manufacturing process, that might change, right? Even if it's 20.001, there is a bit of discrepancy between what I expected the manufacturing to do and what the reality is. But the problem is that those small changes might sometimes significantly change the output of a system. In terms of icing, let's say, or any sort of deformation in the aircraft wing, that might also change, right? So this is important to consider. So this is called robust optimization, in which we consider that sort of errors at the algorithmic level to minimize their consequences, to minimize their impact. If that's what you're doing, that's what you're dealing with, and that's your challenge, you should be looking at the literature of robust optimization. Again, these are all a small active area of optimization that you can explore. I don't know what your complexity is at the moment. If you have an optimization problem, at least now after this part of my talk, you know how to identify your inputs, understand the challenges that you have to deal with, and I'll give you a bit of tips and directions which area of optimization you need to look at. And that's all. That's all I wanted to cover when it comes to the input. Now let's zoom into the constraints. What about the constraints? What are the complexities when we deal with constraints? I might just zoom out a bit. Hang on, no, that's not a part of the slides. It's supposed to be outside, right? So highly constrained landscape. Really, when you have a large number of constraints, the problem is that I might just hang on. Can I maximize this? Let's do it. Yeah, there we go. So when I have the constraints, I will show you an example later on. When you have a lot of constraints, the problem is that you always violate them. You keep violating it, and it's very frustrating. And for example, in an evolutionary algorithm, genetic algorithm, I was working on a problem. Even after 200,000 iterations, or 200,000, I should say, random points, I couldn't even get a single solution to start with. They were all violating constraints. For that sort of things, there are strategies like people feed the algorithm with some feasible solution to start with. Some try to run the algorithm until they found a population and then feed that population again. There are things you can handle that sort of complexity with different techniques. So there is a field called constraint optimization, in which we design techniques how to handle the constraints, how to apply penalty functions, barrier functions, and so on. Constraints are divided in equality and equality and inequality. Let me grab this laser. I think it will be much better. And sometimes some constraints are hard constraints. That means you have to meet them. Some of them are soft constraints, which means if you really violate them at a certain degree, it doesn't matter. It's nice not to violate them, but if you violate, it's not gonna make a big drama. So just to understand what is equality and inequality, let me show you an example. Right? Let's say the designer asked me to create a rectangular table, right? What does that mean? That means length and width should be equal. So by just adding this small constraint, see how the size of search space changes? It's now much, much narrower than what we started with. And obviously that makes the whole optimization process much, much more challenging and much, much harder, okay? And usually constraints divide the search space into two areas, feasible and infeasible, and we want to avoid those feasible. And in reality, in real world problems, this is what you're dealing with. We call them isolated regions or isolated islands, which means you can imagine if you want to survive in this ocean, right, and you want to find some food, the food is there, but when you start, you have to swim across the ocean and go from here to there, and you have no clue where the food is, and you need to find the food to survive. It's very similar to in an algorithm. We need to start from somewhere, but then we need to jump from here to the other region, and how you cross that region, that can be done with penalty function, with randomization. There's a wide range of techniques that you can use. Again, out of the scope of this talk to go through the details, but now hopefully you understand the complexity that people deal with in the field of constraint optimization. So I think that's all I wanted to talk about for the inputs and constraints. Now let's focus on the objectives. One of my most favorite areas in optimization is multi-objective optimization, in which we are trying to maximize or minimize more than one objective. That's one complexity. As I said, when I have one search space, then there is one search space, right? It's like one objective that I have to deal with. But think about it, I might have 5, I might have 10, I might have 20. And that's what makes it a lot more complicated. And often those objectives are in conflict, which means if you satisfy one, if you try to maximize one, the other one get minimized. And I assume that minimization is not desirable. The objectives might change. And usually in real-time application, you're dealing with dynamic optimization or objectives. For example, robot path planning or robot navigation. You constantly get, the landscape from the camera, and it can change, 60 times per second if your frame rate is 60 FPS. Okay, so what does that mean? That means the solution might change also over time. If my robot look away from the target, then I'm going to lose the target. If there's a bit of noise involved, a haze environment, those are the sort of complexity that we deal with in dynamic objectives. So there is a subfield in AI and optimization called multi-objective and many-objective optimization. I've done a bit of work in the past, and that's where we try to address multiple conflicting objectives. And usually for these kind of problems, you don't have one solution, although you can aggregate the objectives to find one, but usually you are looking for a Pareto optimal solution. Okay. A large number of objectives, really, that's state-of-the-art techniques struggle when you have a large number of objectives. So that's why people solve problems by aggregating the objective, by handpicking some of the objectives. And again, that's a very active area. If you're just about to start your PhD and you're interested in optimization, you can easily find a lot of gaps in larger scale optimization, whether it's in objective, whether it's in the constraints, or whether it's in the decision variable. And there is a lot more. Really, I don't have time to get into the details. And one more that I haven't included here, but that just came in my mind, is called expensive objective function. Like, if your objective function take ages to calculate, then you might need to replace it with a meta model, surrogate model, and that sort of techniques to be able to at least get some results, and then you can validate it with the actual objective function. Okay, and as you know, in the evolutionary algorithms like genetic algorithm, particle swarm, etc., you are dealing with a population, which means you need to run the optimization problem multiple times or system simulator multiple times, and that might take ages. You can use parallel computing, but usually people try to use meta models, although they are less accurate than the actual model, but they serve the purpose. And we compromise the quality over the speed, which we have to be able to speed up the whole process. So let's have a look at the example of the table design. Now, let's say I want to minimize weight and also the price, right? I assume, again, this is just a conceptual example. I multiply length and width, and I assume, let's say, each square meter of the table worth $10. Whatever, I don't know. Doesn't matter. As long as we now know there are two objectives. Okay. So let's take a look at this example. If I have two tables given weight and price, the first one is 2 kg, $100, not $100,000. It's a gold probably made table. The right one is 5 kg, $20. Which one is better? So if I ask you, if I'm a client, right, or and I ask you to give me, find a good table for me, design a good table for me, which one would you pick out of these solutions? It's hard to say, right? If your priority is weight, okay, if I want to, for example, use this table in an airplane, right? Commercial airplane, for example, the weight is important, more important than the price. So I'll pick 2 kg. Let's say usually in military applications, money doesn't matter. Money is the least priority, right? Usually the other objective are the highest priority. So I'll pick 2 kg. But if I'm on budget, I'll go to, I don't care, this is 5 kg as long as it's cheaper. But what I'm trying to say is that if I consider both of them, I cannot say which one is better. Both of them are good. it depends on my priority, the client priority, to pick which one. So what I'm trying to say is that we cannot use those relational operators anymore to judge which one is better than the other one. In this case, we can use Pareto optimality, okay, which says a design is better than the other if it's better in both of the objectives. Let's have a look at this one, 5 kg and $10. Definitely, you're going to pick this table, right? Or if it's equal in one objective, but better in the other ones. I've got an example of 2 objectives, but you can extend it to 10 objectives, thousands of objectives. So this one, both of them 5 kg, but the left one is cheaper. Of course, why would I waste my money? I say $10 here. $5 and $10 both, but the left one is lighter than the second one. So I'm confident that the tables on the left-hand side are better and desirable over the ones on the right-hand side. But in reality, usually you are dealing with that sort of scenario. And I know the best example that I always think of is when you want to buy a laptop. It's that what makes it difficult is because, you know, one laptop has a better RAM, the other has a better CPU, graphic card, price is cheaper, and that's what makes it a lot difficult to decide which one you want, right? Because, you know, one is better in one aspect, the other is better in the other aspect, and that's why when the retailer want to get rid of, or I shouldn't say get rid of, but wants to, you know, reduce their stock and give it away, they say, okay, if you buy this, I will give you an extra 4 GB RAM. And that it will help you to make that decision and say, okay, now the CPUs are the same. And then I'm going to get a bit of better, you know, RAM with the same price or with the discounted price. Okay. So in the field of multi-objective optimization, we are looking for that trade-off, the best trade-offs between all the objectives. Okay. So look at this one, like this guy over here, the green one is not better than the second one. Why? Because the second one shows better F1 and F2 over it. So this is cooperative optimal solution. And in the field of multi-objective optimization, we are looking for that sort of solution. How we do it, I'll leave that to you. There is so many research going on in that space. If you find this interesting, that's probably then I highly recommend you to start reading stuff. And I've got some books, by the way, before I forget. I've got one book on multi-objective optimization. It's like 60 pages. Springer, I publish in Springer. If you want, let me know. I've got some. I'm happy to give you a copy to read. I've probably, I don't know whether I'm over my time, but I've got 10 minutes to finish this. So we've done the first part. I've taken you through the story of problems, right? Now we come to the conclusion that every optimization problem at the foundational level has 3 main fundamental components: inputs, outputs, and constraints. Complexity is there, of course, but what I'm trying to say is that sit down, think about those components before you choose an algorithm. Because if you don't spend time on formulating your problem, you are going to find a wrong solution, a wrong optimization algorithm. Okay, so now let's talk about optimization algorithm. I'm going to compare conventional and modern optimization algorithms, or deterministic versus stochastic. A quick disclaimer: I'm going to be biased because every now and again I get mathematicians get mad at me in conferences and say, mathematical optimization algorithms are irrelevant, and I agree with them, and there is no argument about that. But I'm a bit biased towards stochastic methods because that's my research area, right? I've got an inherent, bias towards it. And there is no doubt that a lot of, traditional optimization algorithms struggle, although they have, rigor, although they work on a certain type of problem, but when it comes to those sort of complexity, that is where they tend to struggle a little bit. So that's why I take you through mostly stochastic methods. Let's start with the conventional, one of the most widely used conventional optimization algorithm called gradient descent. You've seen this, all the neural network backpropagation is based on, this algorithm, and it's efficient. Don't get me wrong, because as long as your search space is, I don't know why my system started to, probably that's a bit of heavy slide because I've taken these figures directly from MATLAB without, taking screenshot because I like to have the quality. That's why it's slowed down. But anyway, so if you calculate the gradient of a search space, it will lead you towards the global optimum, right? Whether if you follow the negative of it, it will be minimum. If you follow the positive, it will be a maximum. So gradient descent algorithm is good when you're dealing with unimodal search space. What does that mean? That means when you have a linear, I shouldn't say linear because you might have non-linear, you've got a bit of curvature here. But when you have one global optimum, there is no local optimum. Okay? And that means if this is a problem with 10,000 variables and it's still the same shape, I don't recommend you to use any other algorithm but gradient descent. But the problem is that these are not efficient. Yeah, I know we've got gradient, stochastic gradient, we've got randomization, we've got simulated annealing, and those sort of algorithms that help gradient descent, but usually they tend to struggle and get stuck in locally optimal solution in these kind of search spaces. And that's why, and that's where the modern optimization algorithm, when I say modern, that means because they are recent, definitely propose most of them after, conventional optimization algorithm. And the only thing is that they compromise the deterministic nature, right, over reliability in terms of finding, the global optimum, or in terms of, I should say, increasing the chance of finding the global optimum. They are stochastic. They rely on some sort of stochastic. Let me just minimize this. They rely on some sort of stochastic and randomness to be able to guarantee and increase the finding the global optimum. Okay, they give different outputs, but again, that's the price that we have to pay to be able to increase the chance of finding the global optimum. I've got a quick comparison here between deterministic and stochastic. Of course, the advantage of deterministic method is the fact that they are reliable in finding the same solution each time, but that solution might be the local solution. Requires less number of function evaluation, like gradient descent is sharp to the point. It will jump right into towards the steepest slope and will lead you to the global, hopefully global optimum, not always. They are fast, but what are the drawbacks? Local optimum stagnation, low chance of finding global optimum, high dependency on the initial solution, and mostly need gradient, which is hard to calculate usually in real world problems. Stochastic method, they better avoid locally optimal solution. They have high chance of finding global optimum. They have low dependency on the initial solution. They mostly do not need gradient, and some of them don't need gradient at all. What are the drawbacks? They have slow conversion speed. They need to run the problem multiple times because they are population-based, and they found different answers in each time. So you need to have some sort of quality assurance mechanism, some sort of statistical measures to ensure that what you find is the reasonable estimation of the global optimum. And remember, because of the stochastic nature, you usually estimate a global optimum. Because in real world problems, we don't know where the global optimum is, but with enough quality assurance and with using best practices, we can ensure that we are close to the global optimum. To me, a lot of people ask why stochastic algorithms are very popular these days. A lot of people, particularly in academia, talk about them. I would say it boils down into two reasons. One, high local optimum avoidance. Two, gradient-free mechanism. Because they look at the problem as a black box. Remember and that's why some people call them black box optimization algorithm. And at the beginning, I show you the little robot, and now you know why I put it outside. Because for this robot, we don't really need to know the internal mechanism of this problem. All we need to know is to tune the inputs and keep an eye on the outputs and the constraints. So those methods are often called black box optimization algorithm, and that's what makes them quite applicable, because you just formulate the problem and get the algorithm to stochastically look for the global optimum. Now, before I finish off, it's worth mentioning here, yes, there's a lot of algorithms recently, whether it's stochastic or deterministic, doesn't really matter. I'm not here to defend stochastic methods, not really conventional mathematical optimization methods do work in a lot of cases, but I think it's been demonstrated that stochastic methods also have their position in the space in the field of optimization. There are so many algorithms out there. There are so many hybrids. There are so many improvements. There are so many variants of algorithms. And you might be asking why we have a lot of them. Because look, it's been logically proved that we've got a no free lunch theorem, just like machine learning in optimization, that logically proves there will be no optimization algorithm to solve all optimization problems. That means we don't have one solution to all the problems. And that's why people need to adapt, people need to change, and the people need to improve an algorithm to be able to efficiently solve their problem. Okay, and that's what keeps this area very, very active. Now, before I finish off, I'm going to talk about a few other. I'm going to look at this field from a different angle now, because now you know what the problem. Now you know there are so many algorithms, and we've got different classification and so on. What is your role? Usually, your role is to first understand the problem, as I mentioned so many times so far in this talk, to be able to find a right algorithm. And usually, if you don't have that expertise in algorithm, you can talk to expert in that field. There are so many off-the-shelf optimization algorithms that usually are very beneficial, but sometimes you need to tweak them, you need to tune them, you need to adapt them to your problem. And also there are a lot of technical issues. Like I've been working with a lot of people from the sustainable energy field, those people who use a lot of simulators, okay? One of the technical challenges is the fact that those toolboxes or simulators come from simple optimization algorithm, and it's hard to replace them with new ones. So you need to really find a way to do that. We need to employ better recent optimization algorithm. How to do that? It depends on the it depends on the simulator. For example, I was working with a colleague on the optical field. We were trying to design optical fibers and buffers, optical buffers, I should say. The simulator had a bit of optimization. It was very trivial. And we ended up connecting to PSO and other algorithm. How we ended up doing that, we were writing a file. There was a file between the algorithm and the simulator. We write a file, load it to the simulator run it, and write it back to the file, and then pass it to the algorithm. It was so slow, but that was the only way that we could talk to the simulator. That might be the challenge that you would face, and you really need to get over this hurdle. So because finding a good algorithm for your problem might be easy, but getting over this barrier, it's sometimes take few months. And that's what happens. Often PhD students spend the 6 months to get there, to get over these kind of hurdles, which is a part of the the PhD anyways. But what I'm trying to say, those kind of technical issues get in the way. We might think that it's a waste of time, but really once you get that connection, then you can create a lot of models, try to use a lot of algorithms, and see if you can create a new design. Even you can come up with innovative design looking at the algorithm results. And finally, since the optimization algorithm required a large number of simulations, it is necessary to run simulators in parallel. Sometimes licensing doesn't allow you to do so. So that means you have to come up with, you have to find a proper license that allows you parallel computing, or you have to find a way to sequentially pass them or run the algorithm in a different way to speed up the whole process. And that's all I wanted to cover for this talk. Hopefully I'm not over time. I promise to finish this at 45 minutes mark. So quickly, let's quickly recap what I covered. Today's talk was all about optimization problems and algorithms, right? So the main takeaway from the first part was the fact that you really need to focus on those three components. There are many complexity, list them out, give us a piece of paper about your problem, because without them, we can't help you, right? I need to sit down, have a look at your problem to be able to find the right algorithm. And second part was about algorithm. There are so many algorithms out there. To me, it all goes back to, again, the nature of your problem. We've got combinatorial problems, multi-objective problems, single objective, constraint, problem. For each of them, we have, customized functions. You might find it, again, off the shelf and use it, or you might need to, consult with an expert. to make those changes to be able to solve your problem. As I said during my talk, if you found this kind of interesting, that's my website down there. You can get in touch with me. You should be able to easily find my email online. We always welcome collaboration. I've got some of my best collaborators on the call. I'll always be, as they know, and they can endorse the fact that I'm always open to collaboration. I always try my best to, help people who wants, to grow in the area of optimization. So the door is open. I would like to once again thanks the organization committee for the invitation and for your attention. And hopefully you found a little bit of, interesting stuff in this talk. Now, if there is any question, please let me know. Over to you.
Thank you, sir. I have to ask a question from you.
Sure.
And so basically, as you're expert in optimization, and what we are facing right now is we have edge devices such as the drones or the rovers, which are really in real time. And the optimization problem in especially the image processing areas. So we use genetic algorithms. So what are your views on the genetic algorithm used in the edge AI devices for the optimization problems?
So it's just one question again. I have to understand the problem first.
Yeah.
Right? So is your problem a real-time problem? That means changes over time, right?
Yeah.
Look, I think the main challenge that I've seen people deal with is the time, because when you use genetic algorithm, I don't have any, and I would say probably genetic algorithm is the best option for you. But what I'm trying to say is that probably your challenge is that it takes time to converge, right? Even what you're trying to optimize the population size and generation, stuff like that. Look, there is a field of study called meta optimization, which is you employ an algorithm to find an optimal controlling parameters, like because you can fine tune, you can change, let's say 10 iteration, 15. You can manually ramp it up and see where you can, hit the performance. But why don't you? That's an optimization by itself, isn't it?
Yeah.
Right. That's an optimization problem by itself. So meta optimization is where you go double optimization algorithm.
Okay.
And I think to find that sweet spot, there's a bit of, you can do it manually, but if you want to make sure that you hit the sweet spot, find another algorithm and try to optimize. So you get double a genetic algorithm. One trying to solve the problem, one trying to optimize the genetic algorithm that is trying to solve the problem. It's like Inception. It reminded me of Inception movie. You've got multiple layers.
I got it. Okay. Thank you, sir. Thanks a lot for the
No worries, my pleasure.
Handing over to you. Please continue.
Well, there's a private message. Can you explain the working of SAP swarm algorithm? Look, I think we need a couple of hours for that. So as I said, I've got some book chapters on this algorithm. The paper, I believe the first paper is quite informative, but I've got I've got also a book on that, a chapter on that. If you're interested, I might just put my email in the chat window, if you don't mind. So get in touch with me. I'll be happy to give you some resources to study. And I might at some point, I'm in the process of making some courses on these algorithms, some of them. There is a lot of work, to be honest, but keep in touch. I'll be happy to show you.
Thank you so much, sir. Thank you so much for joining in today, and thank you so much.
I think we have one more question from
Sure. Go ahead, please. Is it in the chat window or?
You can ask.
Hello.
Yes, I can hear you now.
Good evening, sir. Sir, my question is, sir, what is the range of the cost in the PSO? Suppose we apply the PSO, and my second doubt is, sir, if you get the negative cost, so this is okay or any problem, sir? So I have two doubts.
So if I get the second question, which is the negative.
Second question is
no, I get it. First question, I didn't get it.
Okay.
What was the
first question is, sir, what is the range of cost in the PSO optimization?
What do you mean by cost? Are you referring to the computational complexity of the algorithm, or?
Sir, when we use the PSO algorithm of optimization, then we get the cost means objective function, like cost as a objective function.
Okay, as the objective function. So now,
Yes,
what's the
yes.
question around that
So
one?
question is, sir, what is the range of the cost?
Oh,
Minimum
range of
and
the
maximum.
cost. Look, usually what I ask people to do is, and the way that I usually release my source code is for minimization problem, right? Always, I assume people are dealing with minimization problem. But if your problem is a maximization problem, you can easily convert it to a minimization problem, right? If I quickly share my screen, so take a look at this sketch space, right? If I multiply by that one, right? If I multiply by -1, do you agree with me that it will be upside down? Which means if I divide the objective by 1, which is a bit risky because you get division by 0, or if I multiply by -1, you convert it to you convert your minimization problem to maximization problem, or vice versa. So to me, when people come to me and say my problem is a maximization problem, but the algorithm is, I would say just multiply the objective by -1, and that you don't have to do anything extra. So that's, I hope that I answered your first question. The range of cost, what I'm trying to say, you can unify your problem, always work with minimization. Of course, when you want to report the result back, you're going to multiply it by -1 again, to get a positive answer. And your second question, I think you said, whether the objective becomes negative or not. Absolutely. Like going back to my example, the range can be, of course, from -infinity to +infinity. It all goes back to the nature of the problem, right? Here I have from 0 to 10, but depending on my equation that I use, for example, that one, the equation that I use here, it can be very different. It can be negative. Right? So that all goes back to the problem itself. We are not the one who define the nature of the problem. That's the problem that dictates its nature to us, right? So if you get a negative number and it's not reasonable, you need to look at the way that your problem is formulated. If you are not supposed to get, for example, negative lift in an aircraft, for whatever reason, it's just an example, then go and talk to the expert who designed the simulator, who did the formulation of the problem. I would say if you don't expect a negative number and you get it, the problem is usually from the way that the problem is formulated and simulated. Yeah. And hopefully that answers your question. Anything else? All right, so I think Dr. Deepak, would you like to say something in the end?
Sure. Kavya?
Yes, sir.
Yeah.
Okay. Thank you so much, sir, for joining us today. Thank you so much for sharing your resources with us. It was surely an interesting PPT to follow. Thank you so much, sir.
Thank you so much. Thank you so much, Dr. Ali. It is an honor for our conference to have you as a keynote speaker.
My pleasure. It was my pleasure. And as I said, I have a great respect for Indian researcher. It's always I see it as a duty to really give back. Because I've built my career by reading their great articles. So that's a small token of appreciation. Thank you so much. Have a great day, and hopefully I'll see you sometime soon. Bye-bye. Bye.
Thank you, sir. Bye, sir. Moving on, we have the next keynote session starting soon. We have Dr. Chandra Kundarakpam. He's a research associate at Montreal Neurological Institute, McGill University, Canada. He's a research associate working under the supervision of Professor Alan Evans. He has 9 years of research experience in computational neuroscience, machine learning, and neuroimaging with applications in understanding the brain and cognitive development. His interest in neurodevelopment emerged at the start of his postdoctoral fellowship at the Montreal Neurological Institute, McGill University in Canada. During this time, he studied several aspects of brain development using a large-scale longitudinal data set of normally developing children and adolescents, namely the NIH-MRI study of normal brain development. This resulted in several papers, new insights into developmental changes in brain organization, brain behavior relations, and methodological advances. With the acquired skill set on developmental neuroscience, he recently started exploring the social and genetic vulnerabilities that may precede atypical brain development, as well as protective factors that might mitigate risk. Broadly, his research is focused on multi-model imaging, genetic and cognitive data towards the better characterization of normal and abnormal brain development. He believes such integrative approaches will provide critical insights towards understanding the origin and etiology of neurodevelopmental disorders such as autism. He'll be speaking on machine learning approaches towards understanding brain development in health and disease. Thank you so much, sir, for joining us today. It's over to you.
Thank you, everyone, for giving me the opportunity for this talk, in particular, Dr. Shaheed. I will share my screen for the talk.
Yes, sir.
Is my PowerPoint share? Can you see my PowerPoint? Visible?
No, it is not visible yet. Please share your screen.
Now?
Yeah, now it is visible.
Okay. Okay, thank you everyone once again. So I am trained as a physicist from Delhi University. So this is a very unique opportunity for me to pay my respects to my alma mater. After my master's in physics from Delhi University, I joined National Brain Research Center at Gurgaon, where I did a PhD in neuroscience. Then I came over to Montreal Neurological Institute, McGill, where I started learning about image processing, computational neuroscience, with applications to brain development. So today I'm going to talk about machine learning approaches toward understanding brain development in healthy as well as in disorders, for example, autism spectrum disorders, etc. Now, when we talk about the development of the human brain, we know mostly from behavioral development. So, for example, a kid, when they start growing up, we mostly see in the infants the use of hands and the sensory motor, what we call as. But as you develop more, you start speaking language, you start thinking, rationalizing, and it's only at the time of adolescence that the child starts having higher cognition, for example, decision making, complex solving capabilities, or extra. Now, all these behavioral developments, they coincide with the developmental changes that happen at the level of the biological synapses and molecules. And these are captured with imaging modalities, for example, magnetic resonance imaging, functional magnetic resonance imaging, etc. As you can see from this animation, this is the part of the brain, the sensory motor cortex, which is the first ones to develop. And this is represented by the color code, where this part of the brain starts losing the thinning. By thinning, it means that there is maturation, that the brain development happens. Now, at 5 years, the sensory motor cortex is where the cortical thinning starts, and it spreads from a backward to frontward pattern. And as you can see, the last part of the brain which matures are the prefrontal cortex, which are essential for your higher cognitive abilities like working, etc. Now, these changes, let me go back a bit more into the biological changes before we actually talk about these amazing parameters who capture the developmental changes. Right from the time of the birth, and even before that, from the time of conception, several biological events happen. The formation of neurons, then the proliferation of neurons at particular gestational weeks. So neuronal proliferation starts at 4 weeks. And then we have the neural migration, synaptogenesis, and there is also, as well as the programmed cell death happening at the same time at different developmental epochs. To illustrate more, this at 4 weeks, we have the particular zone, this synapses, and by 14th week, you see much more development of the neurons and synapses. Now, as I also mentioned, there is programmed cell death also. So as represented by here, in the monkey brain at P8 versus P90 in the visual areas, you see that these green dots, which are the synapses, there is a reduction by the time of P90. So there is synaptic pruning, what's called as also happening along with the formation of neurons and synapses. This is represented more in terms of the trajectories, where in terms of synaptic density, you see from the time of conception, there is the formation of synapses, and then the synaptic elimination starts. So we see an inverted U-shaped trajectory. This was recently shown in the human postmortem brains also, where this is synaptic spine density in human prefrontal cortex, and you can see synaptic formations still around 9 years, followed by the synaptic pruning. So the take-home message from this slide is that development is characterized by both progressive synaptogenesis as well as regressive synaptic pruning events that occur. Now, these trajectories, they happen at different timelines for different parts of the brain. So as shown by behavioral developments, the regions of the brain that mature first are the sensory motor cortex, which start before birth, and these are followed at the last by the prefrontal cortex, which continue on till adolescence. These distinct regional variations, they provide the structural foundation for changes we see at the level of behavior and cognition. So the animation I showed at 5 years, the first regions to mature are the sensory motor cortex, followed by the temporal parietal regions, and the last ones being the prefrontal cortex regions. So if you look at the behavioral developments at 5 years, it's the motor sensory regions, the behaviors that develop first, followed by the development of language, and the last ones being the higher cognitive capabilities. So as you can see, the changes which we see at the level of synapses and cells, they are captured by imaging parameters which can be looked at the level of macroscopic, at the level of millimeter scales. Now, how do we capture this from synapses to the level of macroscopic? Usually in MRI, we take two-dimensional slices, from which using a lot of image processing tools, we reconstruct the three-dimensional volume, and from that we can find the cortical layers, white matter as well as the gray matter, and we can find measures like cortical thickness, surface area, volume, which would, in theory, capture the number of synapses, the number of neurons. It could be a combination of glia and astrocytes, etc. Now, in terms of the pipeline, this is one example, the Siebert pipeline, where the flow chart is as follows. We have the MRI scans, which the first step is to map to a stereotactic space. This is to enable, this is just like bringing it to the origin XYZ coordinates so that it's comparable across populations. This is followed by a normalization step where, since the algorithms are based on image intensity difference, the first thing is to correct for the intensity difference. Then the next step is to segment the images into white matter, gray matter, and cerebrospinal fluid. And that is followed by classification of the surfaces. So the outer layer being the gray matter, inner layer being the white matter. So this is a gray matter surface, white matter surface, and the difference we can represent as the cortical thickness is ranging from 0 to 7 millimeter. And once that is done, we can use that as a value to regress across population, across behavior, or across disorders. Now, people have quantified this to make sure that these automated measures of the brain match with the post-mortem actual biological measures of the cortical layers. And this is to show that they do correlate, although there are certain regions of the brain, for example, the prefrontal gyrus, where the association is poor. Now, I have been involved with my supervisor in a large NIH MRI study of brain development. It was done in the US for over 10 years. Data were collected across 6-7 different sites, and children from 0 to 22 years were scanned. A lot of behaviors were collected. And to show an example, T1 weighted image, T2 weighted image, diffusion tensor imaging, FA were collected for 1 week, 3 months, 1 year, 2 years, so on. And these were used to produce a series of landmark papers. For example, Nitin Bhakte from UCLA published this landmark paper where he looked at the change in gray matter from 5 years to around 20 years. And as I have explained before, he saw a very nice change from the backward to front propagation happening with development. And in terms of trajectories, we can see that in each region of the brain, we can plot the cortical trajectories, and they have different trajectories. For example, most of the places have linearly decreasing trajectories, whereas some places have quadratic and cubic trajectories also. This was followed by another landmark paper by Philip Shaw, published in Nature in 2006, where he saw that these cortical developmental trajectories relate to the development of cognition also. For example, in particular, intelligence, quotient, IQ. So what I have shown here is the group difference in cortical thickness between children with superior intelligence, which is defines IQ more than 120, versus children with average intelligence, IQ less than 80. And the color codes represent the difference in group cortical thickness, with the warm colors representing more cortical thickness, more brain structure in children with superior intelligence, whereas the blue colors represent the reverse, more cortical thickness, more brain structure in children with average intelligence group. And as you can see at age 7, the cortical thickness or the brain structure was more in for the children with average intelligence, and the group difference vanishes around 8-9 years, but they start coming back with more cortical thickness for the superior intelligence group from around 10 years till 16 years, with predominantly in the prefrontal regions. So what this highlights is that in terms of trajectories, this blue trajectory, it represents a much more dynamic cortical trajectory pattern, with thinner cortex in the beginning, with more cortex around puberty, followed by a faster thinning also. So this goes on to highlight the usefulness of looking at brain trajectories in terms of behavioral cognitive development also. So I look at how this can be used to understand brain developmental disorders, for example, the autism spectrum disorders. So as you might know, autism spectrum disorder is a collection of neurodevelopmental disorders, and it's characterized by large heterogeneity. There is a high comorbidity between autism spectrum and Asperger's, as well as schizophrenia, ADHD, etc. So there is, it's characterized by three main characteristic patterns: social communication deficits, language deficits, as well as repetitive behaviors. And in the US, 1 in 68 children is diagnosed as identified with ASD. In fact, the latest figures show it's 1 in 59 children. Now, what I have done here is, in my study, we use the idea of the cortical trajectories, and we look at whether children in ASD versus healthy children, how does the development of the brain differ with time? So I have shown here from age 6 to 35 years, this is the lateral view of the brain, the left hemisphere. This is the lateral view of the brain, the right hemisphere. This is what's called as the medial view. And this is, if you look from the upper superior view and the inferior view, if you look from below. Now, the colored code represents that the warm colors, more cortical thickness in ASD versus controls. And on the second column, I have shown what's called as the corrected for multiple comparisons. As you might know, these are comparisons, group difference comparisons at more than 80,000 vertices, locations of the brain. So one needs to correct for these multiple comparisons, and these are done with random field theory as well as false discovery rate, etc. We can discuss more about this later. And here you see the reasons with significant group difference over time. So if I play the video, you would see that in the beginning at 6 years onwards, we have much more greater cortical thickness, predominantly on the left hemisphere in ASD, a bit on the right hemisphere also, and this survived the comparison for multiple comparisons. So you can see a lot of the reasons. One more thing I want to highlight is that this part of the brain, which is around here, is what's called as the arcuate fasciculus. These are important for the language comprehension, language development, etc. So I will come back to this part. In terms of a snapshot, as I mentioned, we see more cortical thickness, more brain structure in the brain for the ASD from 6 years till around 14 years, as you can see, predominantly in the left hemisphere around the arcuate fasciculus, implicated in language development, and a bit on the right hemisphere, etc. Now, how does this explain in terms of the biology? So if you plot the trajectories, you see more brain structure, cortical thickness in the ASD compared to the controls. And these indicate that the normal thinning, the normal synaptic pruning, which is supposed to happen, the gray matter maturation, which is supposed to happen, they are delayed in ASD. So there is, that's why you see a thicker or more brain structure in the brain. And this goes along well with the idea that has been shown by other researchers that when you measure the brain size, the whole gray matter volume, there is a brain overgrowth in ASD. Normally, it's been observed that the size of the brain, the head is bigger for the ASD. So there is this idea of the brain overgrowth theory that from birth onwards, the brains of ASD children, they are more and they normalize later on. But our study has shown that this brain overgrowth theory actually goes on till at least young adulthood, so that there is delayed maturation in ASD. Now, as I mentioned before, these are a lot of the reasons around the hardware fasciculars which are implicated in language. So we went to see whether it has any functional consequences. And we did see that in these regions of the brain, the difference in these brain alterations, they related to autism severity, specifically the adult social communication deficit, which is related to language development. So this went on to show that the use of looking at brain trajectories, it can inform us about the developmental disorders like autism spectrum disorders. Now, in order to make it more relevant to the present talk, what I have shown so far and what people have done mostly is if you have the brain scans, the imaging scans of subjects, in particular children, we can plot against A's and we see the trajectories and we infer that how that's deviated in terms of in neurodevelopmental disorders like autism. But recently, so that's modeling brain by A's, but recently using machine learning algorithms, and this is where it's more relevant for the present talk, people have used machine learning algorithms to look at the other way around. So if you have brain scans and we want to use machine learning algorithms to say how can we infer about brain development, brain maturity, and its deviations in developmental disorders using machine learning algorithms. So this is illustrated like here, where we can use the information, brain imaging measures from all the subjects to predict A's in a live out subject, and in that pattern we can combine brain imaging measures and machine learning algorithms to predict brain maturity. In one such example, I used the NIH MRI study. So we had data from 308 subjects, longitudinal scans. So they were scanned more than once. So altogether, 679 scans, and they were used to make a machine learning algorithm, in particular an elastic net regression model to predict A's. So what I've done here is TI is the cortical thickness of all the subjects. Say in 308 subjects, I used the cortical thickness from 307 subjects to predict the A's, chronological A's in the one subject for which I didn't use the imaging measures. In this pattern, when we did the work, so here the method was, it was an elastic net regression model where the whole idea is to minimize this elastic net force function. The first part is the lasso penalty and the second part is the regression penalty. And we use this prediction model to predict the biological A's, and we build a model with high accuracy R of 0.84, as you can see, between true A's versus predicted A's. And more importantly, in terms of biological applications, this paper showed that it has more relevance to biological maturity. Let me explain this better. So in this NIH MRI data set, we have what's called as the Tanner scales, which are biological measures of maturity, which measures development of puberty. So scale 1 represents that puberty hasn't started, scale 2 barely started, scale 3 underway, and scale 4 completed. Now, if you see here, these are the children between 12 to 14 which can have this overlapping Tanner scale. So they could fall in any of these scales. So we don't know for sure whether puberty has developed in these subjects because they overlap. But when we use our prediction model, we saw that the higher the predicted age, the higher the Tanner scale was. So for example, in the children at true biological age of 13, the predicted age is around 17, and the higher the predicted age, the higher the Tanner scale was. showing an application, a scope of our prediction model. Now, recently, we work on developing these prediction models for developmental disorders. So we tried to predict autism severity scores in children with ASD using a similar pipeline. And this was done in a way where we had to consider a partial least score based domain adaptation test, because the scans were collected across different sites, so the site had a big effect. So we developed a PLS based domain adaptation test where we use it to a learning stage where to predict the autism severity score. When we applied this combination of PLS, support vector machine, and lasso regression, we were able to obtain an accurate prediction model of autism severity score. So the true severity score and the estimated score with an R of 0.51. And what's more important was when we look at the top predictors of the severity, the regions of the brain that came out, this is the sensory region of the brain, which is hugely implicated in autism spectrum disorder. So this also showed the utility of our work, the machine learning algorithm work. Now, a recent paper from our group also looked at combining different modalities of the brain to infer, to predict brain maturity. So as I mentioned before, normally we use cortical thickness, cortical volume, but we can also use cortical surface area, diffusion tensor imaging, and for that matter, functional magnetic resonance imaging also. And we use the approach of dictionary learning, in particular non-negative projective dictionary learning, to predict biological age. And the methods in here is we can discuss more with our paper. We model the data in terms of class-specific dictionary framework, and as you can see, as compared to other dictionary learning, NPDL, others without non-negative, ours perform better. This is in terms of mean root mean square error. This is in terms of mean absolute error, and our model perform better than the existing models out there. Now, so far, these were used to understand brain development in healthy as well as in autism using some machine learning algorithms. We wanted to see further than that, and the real application of machine learning would be if I have data from visit 1, and if same child is followed up at visit 2, and we look at the change in brain, can this change in brain data be used to predict the behavioral outcomes, the future cognition of the child at visit 3? That would be the real application of machine learning. And for example, the how his academic performance is. Now, in order to test this, I recently started working on, so we need longitudinal data for this, meaning in the same children, we need to collect data across time points. So I use the NISPD data again in 145 children data, visits 1 to 3. We have this many males and females. We look at cognitive behavior for executive function. So in particular, it's called the brief scores, and they are normalized with age, so they don't change. But we want to see how from visit 1 to 3, can we use machine learning to say that the change in brain predicts the cognition at behavior, cognition at visit 3. So for this, we use, we define the slope of the brain change, which is defined as the cortical thickness at visit 2 minus cortical thickness at visit 1 divided by the age. And we use a random forest regression model. And to see whether it can be used to predict the GRIP score recognition at visit 3. And indeed, we were able to obtain a highly predictive model of the GRIP score at behavior at 3. Now, in terms of the brain regions that were implicated, we use out-of-bag variable importance to find out which regions of the brain were implicated. And in 15 components of the brain, out of 15 components, the sensory motor regions were the top predictors, followed by the frontal regions. So this goes on to show that indeed we can use machine learning to look at the change in brain to predict cognition at visit 3. Now, we're taking it further, and we, instead of isolated regions of the brain, we can also look at the coupling patterns, how regions of the brain are coupled with one another, and whether they can be used in a machine learning framework to predict behavior or future behaviors. So in order to do this, we recently developed a methodology where we look at the maturational coupling, how regions of the brain are coupled during development. So between ROI1 and ROI2, we could look at the change in cortical thickness trajectories, and we can define a maturational coupling index, which would measure how similar the trajectories are. And this was validated using the NIH dataset to show that if we put a seed region at the default mode region, it replicates the findings of default mode. So this was more of a validation of our approach. And we use these maturational coupling matrices so that now, instead of isolated regions of the brain, we are looking at the anatomical coupling patterns, association patterns, to look at the coordination across all the brain regions. And if we use these for all the subjects in a machine learning framework, for example, here being the Connectome predictive modeling framework from Synaptic protocols. And here what you do is you have all the connectivity matrices across behavioral measures, and we can come up with the correlation between brain and behavior. And indeed, we found that these maturational coupling matrices, they can be used to predict the behavior. And regions of the brain that came out highly predictive were from the temporal regions, the frontal regions, etc. This was more to illustrate the utility of machine learning tools in understanding brain development, and with possible applications in future for understanding more neurodevelopmental disorders. So I want to highlight that all of this work are possible because in neuroimaging, a recent thrust has been to openly share data sets. So if any of you are interested, these are not exhaustive, but a list of large-scale data sets that have available neuroimaging as well as behavioral as well as genetic data sets. For example, ABCD data set is coming off from US, where more than 12,000 children at age 9 are collected MRI, fMRI, DTI, along with a lot of behavioral measures like IQ, etc., with genetic data, and they would be followed up for the next 10 years. I have been using the NIHPD dataset of 550 subjects, children scanned more than 3 times, and they also have multimodal brain imaging with a lot of behavioral measures. As you can see, there are other datasets also, PING, PNC, ABIDE. This is for autism dataset, as well as Enigma. So if any of you have interest in applying your techniques to brain imaging, you could look up these datasets, or you could write to me and I can help you more in terms of applying your techniques. So I want to thank my supervisor, my collaborators, and my funding agencies, as well as the organizers again for this opportunity. And if you have any questions, let me know.
Thank you very much, sir. Any queries from the audience? Any questions from the audience? You can also, yes. You can also type the message in case. I welcome Professor Valentina Emilia Beles, ma'am. She's our journal chair. Welcome to the meeting, ma'am. Thank you for joining. Any questions from the audience? You can also type the question in the chat section also. Kavya, back to you. So you can just type your email ID in the chat section.
Yeah.
So that if anyone is having any query, they can just welcome Ahmed Joba, sir.
Hello.
Hi, Dr. Joba. How are you?
Good.
Khushi, you can start, please, beta.
Welcome Dr. Ahmed Zuba, reader in Electrical and Power Engineering, Brunel University, London.
I think your voice is very low.
Am I audible right now?
Deepak sir, is that fine?
Yes, you are audible, but your voice is very low.
Okay. We welcome Dr. Ahmed Zuba, reader in
now it is fine.
Electrical and Power Engineering, Brunel University, London. Dr. Ahmed Zuba received his BSc Honors, MSc, and PhD degrees in Electrical and Power and Machine from Cairo University, Egypt in 1992, 1997, and 2002, respectively. He received his doctoral in Science from Brunel University, London. In 2017, he is currently a reader in Electrical and Power Engineering at Brunel University, London. His main areas of expertise include power quality, renewable energy, smart grids, energy efficiency, and lighting applications. Dr. Zuba is an executive editor at the International Journal of Renewable Energy Technology, an executive editor-in-chief of Technology and Economics of Smart Grids and Sustainable Energy, and an editor-in-chief of the International Journal of Electrical Engineering Education. He is also an editorial board member, editor, associate editor, and editorial advisory board member for many international journals. He is a registered chartered engineer, chartered energy engineer, European engineer, and international professional engineer. He is also a registered member of the Engineering Council, the United Kingdoms, the Egypt Syndicate of Engineers, and the Egyptian Society of Engineers. He is a senior fellow of Higher Education Academy, fellow of the Institution of Engineering and Technology, Energy Institute, the United Kingdoms, Chartered Institution of Building Services Engineers, Institution of Mechanical Engineers, the Royal Society of Arts, UK, the African Academy of Sciences, and Chartered Institution of Educational Assessors, the United Kingdoms. He is a senior member of IEEE and a member of the International Solar Energy Society, the European Power Electronics and Drives Association, and IEEE Standards Association. He will be speaking on the topic Energy, Internet, and Systems and Applications. We welcome you, sir.
Let me share the screen first.
Your screen is visible now, sir.
Thank you. Okay, so good morning, good afternoon, good evening, everyone. And I am honored to be with you today, attending the International Conference on Innovative Computing and Communications. My talk today is about the energy internet and especially systems and applications. Just to let you know from where I am coming from or where am I for now, I am based Brunel University London in Uxbridge, UK. This university is a campus-based university situated in Uxbridge, West London, founded in 1966, home for more than 15,000 students from over 100 countries worldwide, 25th in the top 100 universities under 50 years old. We have 3 colleges and 4 research institutes and the graduate school as well. I am based College of Engineering, Design and Physical Sciences. As an introduction, in the 21st century, traditional pattern for energy use based on centralized conversion of fossil fuels have been facing many challenges. And as we can see from the energy crisis up to the environmental pollution and global warming. As shown in our EU Energy Roadmap 2050, it was forecast that more than 55% of global energy demand is expected to be satisfied by renewable energy sources by 2050. In such an era, a sustainable energy supply system with high energy efficiency is required. About the energy internet, it was proposed in 2011. It's a very new topic, which can make full use of distributed renewable energy and improve energy efficiency and electrical power system reliability. And this is what we are looking forward to, what is called the smart grids in the future. The ultimate goal of the energy internet is to realize distributed and renewable energy systems. So the main aim of my presentation today will to highlight on the concept, structure, characteristics, and development of the energy internet. This is what I will cover briefly, because according to the time, concepts and main body for the energy internet, categories of key techniques, key technologies, key technical characteristics, demonstrations and the pilot applications in Europe, and finally, what about the energy internet dynamic simulation? Let us start with the concept and main body of the energy internet. The energy internet is a multi-energy system based on a power system or a smart grid and is designed to fully utilize renewable energy and promote comprehensive energy efficiency. In addition to that, advanced information and communication technology and power electronics technology are employed to improve the system performance and energy quality. As we can see here, the basic structure of the energy internet. The energy internet is the main link in an energy flow system that contains a coupling transformation among at least 3 different forms of energy, as we see in this figure: electrical energy, thermal energy, and chemical energy. through a distributed intelligent energy management system. Wide area coordinated control of distributed energy equipment is implemented to realize the complementary of cold, heat, gas, water, electricity, and other energy sources, and to establish safe, intelligent, and efficient energy systems. And here we can see on this slide the typical energy internet system structure, including different of energy sources such as photovoltaic, solar thermal, micro gas turbines, combined heat and power, or combined cooling heat and power. Categories of key techniques of the energy internets. Let us start with according to the energy source. The energy flows in the system takes different forms, as we saw in the previous slides. So devices dealing with different forms of energy can be separated. The diverse feature of different forms of energy, including renewable sources such as solar, wind, and tidal power, electrical power devices such as electrical storage, electric vehicles, and heat pumps, chemical sources including natural gas, diesel, coal, biomass, nuclear, and so on, thermal sources including solar heat, thermal storage, cooling, hot water, steam, and so on. What about the energy production? So a special feature of an energy internet system is that grids of various forms of energy are interconnected to form a system that can produce energies of specific forms to meet various demands: electricity, heat, cool, and chemical fuels. Furthermore, combined heat and power or combined cool heat and power can provide more than one form of energy, and the combined systems are always more efficient. What about the prime mover? The energy internet system is based on electrical power system that's connected to a thermal system through prime movers. So the combined system can also be divided by the prime mover. Turbine, including micro turbines, gas turbines, steam turbines, internal combustion engines, and the combined cycle gas turbines. Secondly, reciprocating internal combustion engine, and finally, new emerging techniques such as fuel cells, Stirling engines, and the organic Rankine cycle. What about the energy sequence? Due to the location of the system, the energy sequence can be determined by the local energy structure and categorized into two systems. The first, which is the topic cycle system, in which the electrical power is the priority production and is widely used as a common operation condition. Secondly, bottoming cycle system, in which the thermal energy is the major production. In this case, the system supplies an industry that requires a very large thermal demand. What about the scale of the energy internet systems? It is varying. Generally, these systems can be separated into microsystems, regional systems, and larger systems. Moreover, they can also be classified into distributed systems and centralized systems. Let us see the basic structure of the energy internet. Interconnected energy internet grids and the corresponding control system constitute the backbone of the energy internet. So it's not only energy, it is energy and ICT. In the energy internet, power energy is transformed from renewable energy by wind photovoltaic power generation, and a power network is coupled with a thermal energy network by steam turbines, gas turbines, and electrical heating equipment, and is coupled with chemical energy network by biomass power generation, fossil energy power generation, and electrical hydrogen generations. And here we can see in details the schematic diagram for a typical energy internet systems. So you can see the electrical power systems in blue lines, the thermal system in red line, and the chemical system in green line. So this is how it will look like the energy internet, which mainly contains networks with at least 3 different forms of energy, as I stated: the electrical power grid, the thermal system, and the chemical fuel pipeline grid individually form their own network. These networks are coupled through several key devices, which we call them as energy conversion devices, including microturbines, boilers, and air conditioners. Each kind of key device has its own dynamic response. This is why I will highlight later on the dynamic simulation of the energy internet, including case study, characteristics, and corresponding time constants. When the networks are coupled through these devices and a dynamic excitation occurs in any network, the dynamic processes are filtered by the key devices before they penetrate other network. Therefore, studying the dynamic response characteristics of key coupling devices is essential for studying the cross-energy coupling problem in energy internet systems. It's still a long way of research and development in these important topics. Let us see now the different key technologies for energy internet. First, what is called smart grids, and we know this is what we are looking forward to see in the future in our national grids. Second key technology, which is called energy router, and it is important component because of the main energy transmission channel of the energy internet is the power grid. And we can see here how it looks like the energy router in the energy internet in this figure. Third key technology, which is the virtual power plant. Virtual power plants include various distributed power supply, as we can see in this figure: photovoltaic, wind, energy storage, controllable loads, energy storage station, and other objects. Combination of advanced measurement techniques and the communications technologies into an organic whole regulated by a broker or a control systems. Fourth key technology for the energy internet is the cybersecurity. The energy transmission and the scales network of energy internet is highly open. Any energy supplier and consumers are free to access compared with the conservative and the close communication network, such as the traditional power grid and transportation network. It will face a more severe test. Therefore, improving protection technology of the network security and doing a good job of network security protection is of great significance to ensure the safe operation of the energy internet. I am a power engineer, not expert in the cybersecurity topics, but I am highlighting on all of the disciplines needed in the energy internet. And the final key technology of the energy internet is what system planning. So it is necessary to build a highly autonomous, two-way, interactive, safe, and reliable energy internet system from a whole, which should consider these aspects. First, the optimization of the energy structure in the energy internet. Second, renewable energy consumption in the energy internet. Third, the proportion of controllable load and energy storage in the energy internet. And finally, considering the energy policy, the energy market orientation, and the environmental requirements. What are the key technical characteristics of energy internet? First, multi-energy coordination. On the basis of traditional fossil energy power generations, energy internet has increased a variety of renewable energy generations such as wind energy, solar energy, hydro energy, and biomass energy. By means of the scientific allocation of multiple energies, the complementary features enables clean transition and the stability of energy supply. And this is what we are looking forward also to, the energy mix, and hopefully having 100% renewable energy in our national grids in the futures. Second technical characteristic is collaborative interaction among sources, grids, loads, and storage. Using energy routers and intelligent energy management system through the active management of flexible and controllable loads in energy demand side and distributed generations, supplemented by multiple types and multiple forms of energy storage. The collaborative interaction among sources, grids, loads, and the storage is realized. It's a very high interactions needed among all of these things, and it's not easy to be done. In the meanwhile, the coordinated optimization of energy demand and supply and the optimal allocation of resources are achieved. Next technical characteristic, to be highly integrated among multiple systems. Energy internet takes the power system as the core and hub and relies integration with the transportation system through the vehicle to grid, with natural gas systems through natural gas power generation and the power to gas, with heating systems by the combined cooling, heating, and the power technology. The various physical devices involved in the above systems are also integrated with information communication systems by means of energy hub to realize the integration between the energy flow and the information flow. Also, one of the technical characteristics of the energy internet is the wide area integration among a massive equipment. Energy internet deeply interconnects wide area and massive distributed equipment such as power generations, energy storage, and flexible loads, achieving end-to-end diversified energy sharing and energy open market, improving management, refinement of demand-side resource, and the economic operation level of energy systems. Let us see what is happening in Europe now. And this is key examples for the projects in Europe. The first, what is called e-energy program in Germany, and this was during 2008 to 2013. The German e-energy program successfully demonstrated all of these projects, as we can see. So for the first one, this is electricity market-based virtual power plant with wind and PV power plant, a combined heat and power station, 2 industrial cooling plants, and 450 residential customers. One of the others, which is IDEMA, this is a demonstration of end-user involved virtual electricity trading platform solution within local communities. Rig mode, no, let us do, yeah, I remember me, Regio. This was demonstrated optimal electricity network management through price-based demand response. So the rest is the same. We are talking around the same story, but all of these solutions to a large degree proves the value and visibility of the energy internet solutions for the electricity sector and paves the way for further developments that aim to integrate multiple energy sectors with the intelligent use of digital solutions. Let us see what is happening in Denmark. Energy Lab Nordhaven is a Danish lighthouse project, as you can see here, the map of it, to demonstrate the new European integrated energy infrastructure and solutions in central Copenhagen with a total investment of 143 million. A number of innovative technologies and business solutions were developed over 5 years from 2015 to 2019. And this project shows a best case example of how stakeholders from different industries and sectors can collaborate to develop and demonstrate future energy solutions. This is the other project about the digitizations of district heat in Harrods, following the large-scale deployment of smart meters in the electricity sector. This has been an accelerated rollout of digital solution in other energy sectors, such as heat in 2017. The utility of Denmark's second largest city completed the implementation of 56,000 remotely and hourly read heat meter. In addition, the collected big data are used to improve customer relations and to optimize network investments. There are also many projects, as you can see here in the coming 3 slides, and what are these projects for. So Denmark is heavily involved in the energy internet. We can see France talking about the visibility and the benefits of converting fixed speed pumped hydro storage into variable speed solution. And this is one of the technologies, emerging technologies for the energy storage. As you know that this is a very timely and important topic for the future networks. UK here, my country, we have some projects, as you can see on these slides, including peer-to-peer energy trading, which we call the consumers as prosumers in the future network, implementing energy meter and the billing platform using blockchain, and also tool set for the multidisciplinary design of cyber physical system for smart energy control in buildings and districts. Also, we have some projects, as you can see here, talking about the Internet of Things, talking about distribution network solutions. And as you can see, the size of the energy internet projects in Europe. This is not only Europe talking about energy internet. During the recent years, we can see China is heavily involved in the energy internet, as well as Japan, which is talking about digital grid as well. And lastly, the energy internet dynamic simulation. Let us see what is the foundation of the energy internet dynamic simulations. First, power system and the smart microgrid simulation. Currently, power system simulation techniques have become relatively mature. We don't have a problem in the simulation of the power systems. As you can see, we have tens of the software which helped us in different simulations, including electromagnetic transient simulation, electromechanical transient and the quasi-steady state simulation, middle and long-term dynamic simulation, steady state simulation, electromagnetic, electrochemical simulation, interface techniques, all of these to meet various demands and conditions. Based on power grid simulations, simulations of microgrid have been developed through modeling and introduced to some applications. Also, the microgrid simulations provides a basic model and algorithm for simulating the energy internet system. What about the renewable energy, or mainly the distributed generation or distributed resources and smart microgrid simulation? We have two parts for the steady state analysis, and this is solving the steady state operating point of the system according to the given operating mode of the distributed resource system, and obtaining the fault current by short circuit fault analysis, which provides the basis for selecting equipment and the switching capacity. And we don't have a problem, as you know, it is well established simulation for the power systems. We have transient stability simulation, which focus on the relatively slow dynamic processes of the system with simplified network components, power electronic devices, distributed power supply, and various controller models to model and simulate the system using quasi-steady state model to describe the system. And finally, we have what is called fine simulation of device behaviors, which pays more attention to the faster and the more precise features of the smart microgrid or equipment. What about the other two systems, which are chemical systems and thermal systems of the energy internet? Here I call them as non-electrical power system simulation. Thermodynamic system equipment is diverse and its dynamic response crosses over a wide time scale. The model is described through a set of algebraic equations, ordinary differential equations, and the partial differential equations with distributed parameters. These equations with their solving algorithms can cover the key technologies of energy system modeling and simulation, which are representative. Modeling and simulation of thermodynamic can broadly divided into two levels: simulation analysis for devices and simulation analysis for the whole system, which will be divided into static simulation and dynamic simulation. And finally, the energy internet system simulation, which will still developing. We don't have well-established simulation for the whole energy internet system as a whole, and this need to focus on the combined heat power and the combined cold heat and power. What are the application scenarios for energy internet dynamic simulations. Dynamic simulation techniques can be applied in the field of the energy internet, just as they can be applied in electrical power systems to achieve scheme verification, accident analysis, countermeasure making, skill and operation training, and so on. We have several application scenarios, and here sample of them. First, basic theory research and validation. Second, verification of the planning and design scheme. Thirdly, research and optimization of control strategy. Fourth, adjustment to the configuration and operation mode. And finally, others such as hardware in the loop, online system security assessment, training of operation and the maintenance staff, fault reappearance, and countermeasure formulation. Here we can see the fundamental differences in modeling and solving for various forms of energy. And as you can see, I concentrate in this last topic to open the door for the researchers in this topic. The first difference, the modeling and the calculations of coupling among equipment and between equipment and network. There are essential differences in the coupling mechanisms within energy grids and different modeling and the calculation methods of coupling among equipment and between equipment and network, all pose difficulties to dynamic simulation of the energy internet. The main body of the electrical power system, as we can see in the previous slides, the generators, the exciters, the speed regulators, transmission and distribution networks, power electronic devices, and finally the loads. The main link or coupling link of the electrical power system is the grid itself. So here it is clear everything as power engineers. In comparison, the scale of the thermodynamic system is relatively small, the number of equipment components is limited, and the coupling among equipment components is more direct. Second difference, the strong nonlinearity or nonlinear algebraic equations. Dynamic models of an energy network and the elements includes two sections: algebraic equations and differential equations. Nonlinear factors mainly exist in algebraic equations, which makes it difficult to solve energy system models. The conversions and the convergence speed depend on many factors, such as initial values of unknown variables in the equation, the iterative flow, and the method for accelerating the convergence. There are obvious differences in nonlinearity sources and the processing method of nonlinearities in different energy systems. And finally, as a key difference, long dynamics from radial state change of working medium and multi-physics integration. The overlapping of multi-time scale physical processes of some dynamic components in electrical power systems creates substantial difficulties in modeling and the model parameter acquisition. Long dynamics can also be observed in energy component when radical change occurs in the working fluid state. The overlapping fusion of multi-scale physical processes increases the difficulty of the system modeling and simulation, and it is difficult to establish a set of models that can be adapted to the whole dynamic processes in the equipment system level simulation. Let us see this interesting case study. And the case study includes an existing energy system of a large building was extended by integrating a micro gas turbine in which the thermal energy of the exhaust gas via a heat exchanger was used to contribute heating the building. The nominal power of this micro gas turbine was 100 kilowatt, and the turbine was controlled by prescribing a set point for power output. The heat extraction in the heat exchanger was performed by water and controlling the inlet temperature to the heat exchanger to ensure that the limit values for the water temperature were not exceeded. The system was in operation, healthy, for some weeks before it couldn't be restarted after an unexpected shutdown. And why this unexpected shutdown? We can see what was happened. Overheating in the combustion resulted in melting metal deformation and further damage. And we can see here, zooming, we can see the turbine inlet, spiral penetrated from the inside, and also we can see here turbine parts in the inlet spiral. And here, as we can see, the complete failure which had occurred due to the overheating. The combustion parts entered the high-speed turbines, which was damaged, and parts of the destroyed rotor penetrated the inlet spiral to the turbine. We started a root case analysis, and it was performed, which included evaluating the history of the installation, analysis of operational data, and modeling and simulation. Processing the collected historical operational data resulted in this graph, which you see on this slide, which is similar to the zoomed one in the next slide. The data were collected by the control system and had a resolution of approximately 1/30 seconds. The power output that follows the set point, the relative rotational speed, and the water temperature in the waste heat recovery heat exchangers are visualized. If we concentrate on the zooming on what was happened exactly on 29th of January 2011 in this area, we can see here the zooming in graph. It is interesting here to observe the fluctuation in the water temperature, which are after exceeding a certain amplitude followed by changes in power output and rotational speed. In some cases, the rotational speed decreased well below 50%, and the engine shut down, followed by an automatic restart. The failure of the engine was evaluated to be caused by flashback of the flame during the large fluctuation in the rotational speed, which was possible because the combustion was of a lean pre-mixed type, and reduced airflow might have resulted in flame speed higher than the flow velocity. Such conditions allowed the flame to propagate back into the pre-mixing zone. The flashback led to overheating and melting material and material breaking as well, entering the turbine, which caused complete failure. But after all of that, there is a question remained about the cause of the fluctuation, because the micro gas turbine was considered robust and stable in several other applications. We can see that the main reason that the failure occurred was the integration of the micro gas turbine without considering the dynamic processes and the inbuilt control systems. If these considerations had been accounted for in an early stage, corrective actions could have been taken. And here, just to conclude, why the importance of the dynamic simulation of the energy internet as a whole system. So that's it for my talk, concluding with a very brief conclusion. I like it. The internet is changing the energy cycle from petroleum-based to solar electric and moving into space. Just to highlight, this presentation is a part of my book, which was published in 2020 by Springer. This textbook is the first of its kind to comprehensively describe the energy internet, a vast network that efficiently supplies electricity to anyone, anywhere, and is an internet-based wide area network for information and energy fusion. I thank my co-editor, Professor Zhanhui Shao from China, and I thank all the contributors in this book. Thank you.
Thank you, sir. It was a very insightful and informative session. Thank you for gracing us with your presence. I feel very honored to introduce our General Chair of ICICC 2021, Professor Valentina E. Ballas. Professor Valentina E. Ballas is currently a full-time professor in the Department of Automatics and Applied Software at the Faculty of Engineering, Valladolid, University of Arad, Romania. She holds a PhD cum laude in Applied Electronics and Telecommunications from the Polytechnic University of Timisoara. Dr. Ballas is the author of more than 350 research papers in referred journal and international conferences. Her research interests are in intelligent systems, fuzzy controls, soft computing, smart sensors, information fusion, modeling, and simulation. She is the editor-in-chief of the International Journal of Advanced Intelligence Paradigms, IGAIP, and to International Journal of Computation Systems and Engineering, IGCSE. A member in the editorial board or member of the several national and international journals, and is evaluator expert of national international projects and PhD theses. Dr. Ballas is the director of Intelligent System Research Center in the Valladolid University of Arad and director of Department of International Relations Programs and Projects in the same university. Now she is working as a national project with European Union funding support BioCell Nano Art equals to novel bio-inspired cellular nano architectures for digital integrated circuits, 3 M euros from National Authority of Scientific Research and Innovation. She is a member of the European Society of the Fuzzy Logic and Technology, a member of the Society of the Industrial and Applied Mathematics, and a senior member of IEEE, a member of the Technical Committee, Fuzzy Systems, IEEE Computational Intelligence Society, chair of the Task Force 14 in Technical Committee, Emerging Technologies, IEEE CIS, a member in the Technical Committee, Soft Computing. Thank you so much, ma'am, for joining us today.
Thank you very much for the presentation. And ladies and gentlemen, dear colleagues, dear students, I'm very happy and I'm glad to be here with you at the closing ceremony of the important conference that you started a few years ago. It's about International Conference on Innovative Computing and Communications, where you introduced me as important chair of the conference, general chair. Thank you very much once again. First of all, I want to express my appreciation for this kind invitation. Then I highly appreciate your work. It's a great work, receiving 900 papers and accepting 207 papers from more than 20 countries. This is a huge work. So your team is a successful team. I want to tell you some words at this closing ceremony because I was inspired by the speech of Professor Agarwal, NBA chairman and chief guest of this conference. I was looking many presentations on YouTube after the conference, and this speech inspired me because he said the truth that we are producing a lot of papers, but we need to have practical applications. That means innovation, inventions, and so on. First of all, I want to tell you about some words from a very well-known inventor, Romanian inventor, Henry Marie Coandă. He was living between 1886 and 1972. He was born in Bucharest. He was living a lot in Paris and so on. And he is an aerodynamic pioneer and builder of an experimental craft. The Coandă effect is well known. This craft was made in 1910. He described Coandă effect in the mid of 1950 as the first jet. So our jets are going now flying using Coandă effect. There are some disputes here, but he is well recognized. He invented a great number of devices, designed the flying saucer, and discovered the Coandă effect of fluid dynamics. So he said, I saw also recently on LinkedIn, but I knew this story. He said like this: man does not advance towards the future as seen, but with his back forward like a rower. He does seize the past, but not the future to which he is advancing. Considering if at the helm of this vessel where he works, there is one who looks from time to time, then the same sees from time to time an invention, and thus that's development. So it's a reality that we need from time to time to have such important development and invention that will move toward the humankind. But also, I am inspired by your scientist, an Indian scientist, Ramesh Mashelkar. You know what he said about innovation. So innovation is the successful exploitation of a new idea. Through innovation, we achieve more from less for more, getting more performance from less cost for more people. This conference is oriented towards increasing benefit to mankind, at the same time conserving our ecosystem. In my travels in India, I saw everywhere all teams in universities, research teams working very hard and showing me in every university their invention from the student side. And I was very happy to see so many ideas, very simple, very easy to organize, and the pragmatism that is there, but also the humanity side of their inventions. So they were many oriented for many people, so for using for more people. As I said here, your scientist Ramesh Mashelkar said. So achieve more from less for more people. But it is true that sometimes these inventions in the first stage means a lot of money to invest there, because you need to move to a new technology, to something new. So in the first stage, it's important to invest money, and then you will see decreasing the price. As I told you, I saw many inventions that were proposed for poor people to have some devices for them for a very low price. So I like very much this attitude. I want also to tell you, because here in this conference, there are mainly young scientists and students, PhD students, young professors. I have some advices for them. So first is related to relationships. These are everything. So you need to have relationships. Like this team in this conference, Dr. Deepak Gupta and Dr. Ashish Khanna has a lot of relationship everywhere in the world, and they can move very fast. They can organize, they demonstrated, they can organize a conference in Europe. It's not a problem, with good scientists, the best in the world. And so this first point for your team, this conference is achieved. Then never stop learning, and never stop learning how to learn. This is very easy because we have this infernal tool that is internet. We have everything on internet. You need only to dedicate your time to stay and to study, to discover your direction, your right direction, and to work very seriously there, and not to produce a paper, but to produce also some inventions. So look to some facts that can be applied immediately, be pragmatic, and do your job until the end. And the third advice is be a problem solver. This time is a challenging time, but for those of us who are able, I encourage you to see if there are also opportunities here to make a difference. Explore problems that are important to you. Think about the steps you might start to take the begin, attacking the problem head on. It is true, I was working for 9 years in a big factory. And the other half of my team, my husband also, he was working in pure research. I was working in design and research. So having these practical things in your hand, it's very easy to move forward and to be a good teacher, to teach your students to be practical in their research. So not all are doing like this, because many of you are working immediately in education, but you have this big opportunity to access many projects. In India, there are so many possibilities. Also, I can see that there are many projects, joint projects from India to Europe. Unfortunately, until now, I cannot find India, Romania, but you must know that I'm fighting for this. And my friends from India ask me many times, please do some, by your relations, do some connections in Portugal, in Hungary, in Austria, in countries in Europe. Of course, I can do this. And I was successful with many professors from India. They have projects, they are very happy. But I heard that just nowadays, our ambassador in India will be a woman. And I started to discuss with her, and I hope to be successful, not over Erasmus project, because I want to see many Indian scientists here in Romania. Also, you know that in Bucharest, we have now the big center for cybersecurity in Europe. So European Commission named Bucharest as the capital for the next year, in next years, and there will be a big amount of projects, and I hope to see Indian teams working with us here in Romania. Why not? I will come back to the theme of this conference, and I really appreciate and congratulate Deepak and Ashish, because they are very, very dedicated people for their work. Their conference in India and in Europe, organized there in Czech Republic, is well known, and I hope to see them also in Romania in my university. They are a very well known name in India, and they can attract so huge number of papers. That means they are very trustful persons, and their work is very much appreciated. And I saw in this conference volumes in Springer. It's a very important thing, because Springer is publishing in a very high quality book series, also many special issues in important journals. This is a very important help for all scientists there in India and also in other countries, because we can also benefit on this. So I congratulate you once again, and your team, your reviewers, your students that were with you. I saw very nice girls presenting here the conference. I like to see women. I saw also in the opening ceremony very important scientists from India. All of you deserve my congratulations and the big medals. I invite you to continue to work very seriously for the benefit of humanity and for the better future. And I hope to see in person, maybe in few months, because you started in this conference. I saw you face to face. I'm so happy that you are encouraged, and maybe your vaccine is very good and permit you to be together. I was also recently invited to a wedding there to some good friends. I told them I cannot go, but I love to be with you. And I know them from Siliguri. And I asked them, how many people are there in your wedding? 500. Oh, so many, because here maybe 10, 20. So it seems you are moving in a good direction. And I wish you good luck for all your events. I will be always with you, helping with what I can, and hope to see you in India and in Romania too. Thank you.
Thank you so much, ma'am.
Thank you so much, ma'am, for gracing us with your presence. That was a really encouraging session. Finally, we're approaching the end of the two-day program of the ICICC 2021 conference. It is my pleasure to invite Dr. Ajay Jaiswal, sir, to take over. Dr. Ajay Jaiswal is currently serving as an assistant professor in the Department of Computer Science of Shaheed Sukhdev College of Business Studies, University of Delhi. He is co-editor of 2 books and journals and co-author of several research publications in international journals and conference proceedings. He has completed an interdisciplinary project titled Financial Inclusion Issues and Challenges, an Empirical Study, as SCOPUS. This project was awarded by the University of Delhi. He obtained his master's from the University of Roorkee, now IIT Roorkee, and PhD from Jawaharlal Nehru Institute, Delhi. He is a recipient of the Best Teacher Award from the Government of India of NCT, Delhi. He has more than 19 years of teaching experience. Currently, he is working as co-PI on major project titles, increasing the impact of government welfare policies for social media, for social and financial inclusion through technological integration in India, awarded by the Indian Council of Social Science Research, ICSSR. We welcome you, sir.
Thank you. Thank you for the nice introduction. So good evening to all. As we are knowing that this is the fourth version of this conference, and for the first time, we are organizing this online due to the pandemic situation. And even then, we have put all the efforts, and we can say this conference is actually a great success. From the last 2 years, we are organizing this conference in collaboration with Shaheed Sukhdev College of Business Studies, University of Valladolid, Spain, National Institute of Technology, Patna, and Universal Innovators. And I'm happy to inform you that this conference is growing in leaps and bounds. Every year we are receiving the large number of papers, and this number is continuously increasing. This year we received approximately 900 papers. Out of those, only about 200 were selected for the publication and the presentation. And the proceeding of this conference will be published by the Springer in a Scopus index series. And the selected paper will be selected, and we can say the extended paper will be invited, and those papers will be published after proper review in SCI indexed and the Scopus index journals. So I would like to further inform you that we are also announcing the best paper awards in each of the sessions that we have. We have actually 10 sessions in this conference, paper presentation sessions. And so we will be announcing 10 awards. And these awards will be informed. These awards will be informed to you through email by the 28th of Feb. And at the end, would like to thank you all the organizers, SSCBS, NIT Patna, University of Valladolid, Spain, Universal Innovator, making this event a great success. I would also like to thank our keynote speakers, authors, publishing partners, and sponsors. I would also like to thank our General Chair, Professor Valentina, Professor Siddharth Bhattacharya, and all other eminent persons associated with us. Because of all those persons, this conference is actually the success. And at last, I'm thankful to the Almighty God and seeks blessing that all our future endeavors becomes like this. And with these words, I conclude the proceedings of this ICICC 2021. Thank you.
Thank you, sir.
Thank you, sir. Thank you, Valentina ma'am.
Thank you, Valentina ma'am, for your presence and the appreciation you showered on us. Thank you so much. And I really remember the meeting in Delhi. We met, I think, around 1 or 2 years back, and that was really a very enriching meeting. And you showed us many ways how to improve the research, and many things we discussed at that time. And surely we would like to see you in India once everything calms down due to in this era. So in this COVID era, this is a new normal right now, and but still we tried to do the conference in hybrid mode, and with the advice of Professor Mr. Dr. Jaiswal and Dr. Anand, we did it in hybrid mode. So we will surely, I would like to thank to all the authors for giving us the support. And here I announce that with the best paper award, we will also give certain financial benefits also, maybe in the form of discounts in the future papers. And we will send everything along with the certificate, all the details, and we will encourage all the people who have submitted their good papers in the ICICC. They can again, they all are invited again, and we are also going to organize one conference, that is ICDAM 2021 with Poland, with the Poland University. And it is from India. We have our friend Polwaski is there, and with him we have done the conference last year also. And this year in July, the conference is there, that is ICD-AM 2021. It has also two Indian educational institutes are also backing the same conference. One is the PITE, the Panipat Institute of Engineering and Technology, that is based in Haryana, and one is IISU University from Jaipur. And there the Dr. Rathore is there, who is also a known face in research community. So we are again coming up with another good conference. So we all need your support, and from all the authors, we need the support that you all are going to support us in near future also. So thank you so much. And with this, as Ajay sir has said, that this is the closing time. So goodbye to all of you. Be safe, remain inside as much as possible. Thank you.
Thank you. Thanks to all for for participating in this conference, ICICC 202. Now we are closing this. Ekansh?
Yes, sir.
You can close this meeting.